The Milky Way galaxy is an enormous system that contains billions of stars, numerous planets, and large amounts of gas and dust. However, it is not just a simple flat disk of stars. The galaxy has several layers above and below its main structure, each containing different and less familiar features. Above the spiral arms of the Milky Way lies a vast halo made up of dark matter, old stars, and star clusters that may provide important information about the galaxy's formation. Below the disk are regions filled with high-energy radiation, diffuse gas clouds, and remnants of ancient stars that continue to move through space. Before we continue tonight's cosmic journey, let us know where in the world you're watching from and what the time is for you now. We're always excited about hearing where in the world our viewers are tuning in from. The Milky Way, also known as the Milky Way Galaxy, is the vast cosmic home that contains our solar system. Its name comes from the way it looks when seen from Earth, a faint milky band of light stretching across the night sky. This glowing path is made up of countless distant stars that are so far away that our eyes cannot tell them apart individually. Instead, they blend together into a soft, luminous stream of light that has fascinated people for thousands of years. The Milky Way is a barred spiral galaxy, shaped somewhat like a giant pinwheel with a bright centre and long, graceful arms spiralling outward. Its visible disk is about 87,400 light-years wide, yet only about 1,000 light-years thick where the spiral arms lie, making it extremely thin compared to its enormous diameter. Recent studies and computer simulations suggest that an invisible cloud of dark matter, which surrounds the visible part of the galaxy, might stretch as far as 2 million light-years across. This dark halo may even contain a sprinkling of faint stars hidden deep within it. Our galaxy is not alone in space. The Milky Way has several smaller companion galaxies, called satellite galaxies, that orbit around it. Together, these galaxies belong to a family known as the Local Group, which is part of an even larger cluster called the Virgo supercluster. Beyond that lies the Laniakea supercluster, an immense region of space that holds hundreds of thousands of galaxies, all bound together by gravity like islands floating in an endless cosmic ocean. Astronomers estimate that the Milky Way contains between 100 billion and 400 billion stars, and possibly just as many planets. Our own solar system sits about 27,000 light-years from the galaxy's centre, on the inner edge of a spiral arm known as the Orion Arm. Near the middle of the Milky Way lies a bright, crowded region of stars forming a thick central bulge. At its very heart is an extraordinary object, a supermassive black hole called Sagittarius A star. This mysterious black hole has a mass roughly equal to 4 million suns and exerts a powerful pull on everything nearby. The oldest stars in our galaxy are almost as ancient as the universe itself, born not long after the Big Bang during the earliest ages of cosmic history. The true nature of the Milky Way was not understood until fairly recently. In the year 1610, the Italian astronomer Galileo Galilei was the first to use a telescope to reveal that the pale band of light in the sky was actually made up of countless stars. For centuries afterward, most astronomers believed that the Milky Way contained all the stars in existence, that it was the entire universe. This idea changed in the early 1920s, following the famous Great Debate between Harlow Shapley and Heber Daust Curtis. Then, in 1923, Edwin Hubble discovered that the faint cloudy objects seen beyond our galaxy were actually other galaxies. His discovery transformed our understanding of the universe, showing that the Milky Way is just one among billions. When seen from Earth, the Milky Way appears as a glowing band of white light, about 30 degrees wide, arching gracefully across the night sky. Every star we can see with the naked eye belongs to the Milky Way, but the term Milky Way usually refers to this shining band itself. The light we see comes from countless distant stars and cosmic dust, concentrated along the Galactic Plane. In certain places the band looks brighter, forming glowing patches known as star clouds, the largest of which is the Large Sagittarius star cloud, part of the galaxy's central bulge. Other areas appear dark, such as the Great Rift and the Coal Sack, where thick clouds of dust block the light from the stars behind them. In the southern hemisphere, ancient peoples like the Inca and Australian Aboriginals looked upon these dark areas as dark cloud constellations, shaping myths and stories around them. The part of the sky hidden by the Milky Way's dense band of stars is known as the zone of avoidance because it obscures our view of distant galaxies beyond it. Despite its beauty, the Milky Way is not always easy to see. Its light is fairly dim, and it can be drowned out by the glow of city lights or even by the moon. To see it clearly, the sky must be very dark, darker than 20.2 magnitudes per square arc second, according to astronomers. It becomes truly breathtaking in rural areas when the moon is below the horizon, showing rich details that vanish under bright conditions. Sadly, due to light pollution, more than 1/3 of the people on Earth can no longer see the Milky Way from where they live. When observed from Earth, the Milky Way's glowing path passes through 30 constellations. Its galactic centre, the brightest part of the band, lies in the direction of Sagittarius. From there, the band curves across the sky toward Auriga, opposite Sagittarius, before looping all the way around to complete a full circle, dividing the heavens into two almost equal halves. The Galactic Plane, the invisible flat sheet on which most of the galaxy's stars lie, is tilted about 60 degrees from the ecliptic, which is the path the sun follows through the sky, and about 63 degrees from the celestial equator. Long ago, when humanity was just beginning to wonder about the glowing band that stretches across the night sky, many great thinkers tried to explain what the Milky Way really was. One of the earliest was the Greek philosopher Aristotle, who lived between 384 and 322 years before Christ. In his famous work Meteorologica, he mentioned that other philosophers before him, Anaxagoras, who lived around 500 to 428 years before Christ, and Democritus, who lived from 460 to 370 years before Christ, believed that the Milky Way was made up of the faint light of stars that could not be seen directly. They thought that these hidden stars were veiled by the Earth's shadow, while the stars we could see shone by reflecting sunlight. Aristotle, however, had his own explanation. He imagined that the Milky Way belonged not to the heavens but to the upper part of the Earth's atmosphere. He thought that it was formed by the fiery breath of stars burning high above, whose light did not fade away because it was trapped in the outermost layer of air. According to him, the hazy milky glow that we see was simply the result of light bending, refraction, through the Earth's atmosphere. Many centuries later, a philosopher named Olympiodoros the Younger, who lived around 495 to 570 years after Christ, disagreed. He argued that if the Milky Way were truly a phenomenon within the Earth's atmosphere, then it should look different depending on where or when one observed it. Yet, it always appeared the same. From this, he concluded that the Milky Way was not earthly at all, but celestial, a part of the heavens themselves. This idea would later influence astronomers and philosophers in the Muslim world. The Persian scholar al-Biruni, who lived between 973 and 1048, suggested that the Milky Way was made up of countless tiny fragments of nebulous stars. Around the same period, the Andalusian astronomer Avempes, who died in 1138, claimed that it was indeed composed of many stars that appeared as one continuous band because of the way their light blended in the air. He supported his claim by describing a close meeting, or conjunction, of Jupiter and Mars that he had witnessed around the years 1106 or 1107. Another great mind, the Persian astronomer Nasir al-Din al-Tusi, who lived from 1201 to 1274, wrote in his book Tadhkira that the Milky Way was formed from a vast number of small, tightly packed stars. Because they were so close together and faint, they looked like soft, cloudy patches, giving the sky a milky appearance. Later, the scholar Ibn Qayyim al-Jawziyah, who lived from 1292 to 1350, agreed, describing it as a myriad of tiny stars clustered in the sphere of the fixed stars. Real proof that the Milky Way was made of countless stars finally came in 1610, when Galileo Galilei turned his telescope toward that mysterious band. Through the lens, he saw what no one had ever seen before, a sparkling sea of countless faint stars stretching through the heavens. Galileo realized that what had once seemed like mist was actually a vast collection of suns. Yet, even he still thought the glow was partly caused by the bending of light in the Earth's air. About a century and a half later, in 1755, the philosopher Immanuel Kant, drawing upon earlier ideas by Thomas Wright, made a bold and accurate guess. He proposed that the Milky Way was a gigantic rotating system of stars held together by gravity, much like the solar system, but on an unimaginably larger scale. From our point of view within this enormous disk, we would naturally see it as a shining band across the night sky. Both Kant and Wright even suggested that some of the hazy patches we see, the so-called nebulae, might be other galaxies like our own. Kant called them island universes, a poetic phrase that scientists continued to use well into the 20th century. In 1785, the astronomer William Herschel made the first serious attempt to map the Milky Way and determine where our Sun lies within it. By carefully counting stars in every direction, he drew a rough outline of the galaxy, placing the solar system near its centre. Then, in 1845, Lord Rosse built one of the most powerful telescopes of his time. With it, he was able to see that some nebulae were not just cloudy blobs but spiral or elliptical in shape. He could even make out individual stars within them, supporting Kant's earlier belief that these might be entire galaxies. In 1904, Jacobus Kapteyn, while studying how stars move, discovered that their motions were not random. Instead, they could be divided into two great streams travelling in opposite directions. This finding later helped scientists realise that the Milky Way itself rotates, a discovery that was expanded upon by Bertil Lindblad and Jan Oort, who confirmed the galactic rotation in detail. By 1917, Heber Doost Curtis observed a bright nova in the Andromeda Nebula, now known as the Andromeda Galaxy. When he examined photographs, he found 11 more novae and noticed that they were about 10 magnitudes fainter than those inside the Milky Way. From this, he calculated that Andromeda was about 150,000 parsecs away, far beyond our galaxy. Curtis championed the idea of island universes, believing that spiral nebulae were separate galaxies. This view led to the famous Great Debate of 1920 between Harlow Shapley and Heber Curtis, where they argued about the size of the universe and whether the Milky Way contained everything that existed. Curtis supported his case by noting the dark lanes and dust clouds in Andromeda, which resembled those in our own galaxy, and by pointing out the redshifts in its light. The mystery was finally settled in the early 1920s when Edwin Hubble used the mighty 2.5-metre Hooker telescope at the Mount Wilson Observatory. He photographed the outer edges of spiral nebulae and saw that they were made of individual stars. Among them, he found Cepheid variable stars, which allowed him to measure their distances. His calculations showed that Andromeda lay about 275,000 parsecs from the Sun, far too distant to belong to the Milky Way. It was a separate galaxy, one among countless others scattered across the universe. In modern times, the European Space Agency's Gaia spacecraft has carried on this grand quest. By precisely measuring the parallax, the tiny shifts in position, of stars, Gaia has created the most detailed three-dimensional map of the Milky Way ever made. The results have been described as truly transformational. Gaia increased the number of mapped stars from only about 2 million in the late 20th century to around 2 billion. The spacecraft has expanded the region of space we can measure by a factor of 100 in size, and improved accuracy by about 1,000 times. In the year 2020, Gaia's data revealed that our galaxy seems to wobble, possibly because the disk of the Milky Way is slightly tilted within its dark halo or influenced by nearby smaller galaxies tugging at it with their gravity. And in April of the year 2024, scientists released the first detailed maps showing the magnetic fields threading through the Milky Way, another great step in our long journey to understand the vast glowing home we see above us each night. The Sun, our life-giving star, rests near the inner edge of a region of the Milky Way known as the Orion Arm. It floats within a warm, wispy cloud of gas called the local fluff, which itself lies inside a much larger cavity of hot gas and dust known as the local bubble. This area sits between two great wave-like structures of our galaxy called the Radcliffe Wave and the Split Linear Structure, which were once thought to be part of a ring known as the Gould Belt. Astronomers studying the motion of stars near the giant black hole at the Milky Way's centre, known as Sagittarius A star, have estimated that the Sun is about 27,140 light-years away from that galactic heart. Another group of researchers, using similar methods, found a slightly smaller value of about 25,640 light-years. The Sun also does not lie exactly in the flat plane of the galaxy. It sits roughly between 16 and 98 light-years above it. The next spiral arm outward from ours, the Great Perseus Arm, lies about 6,500 light-years away. Our solar system, therefore, sits comfortably in what astronomers call the Milky Way's galactic habitable zone, a region where conditions are calm enough for life to flourish on planets like Earth. Within a region about 49 light-years around the Sun, astronomers have counted roughly 208 stars that shine brighter than absolute magnitude 8.5. This gives a density of about one bright star in every 2,360 cubic light-years. But when dimmer stars are included, the picture changes dramatically. Inside a much smaller area, only 16 light-years across, there are 64 known stars, not counting 4 faint brown dwarfs. This means there is about one star for every 284 cubic light-years. These numbers show that faint low-mass stars are far more common than bright ones. Across the entire sky, only about 500 stars are bright enough to be easily seen with the naked eye. But when telescopes look deeper, they find about 15.5 million stars brighter than magnitude 14. The Sun is not standing still. It is moving through space. The direction it travels in the Milky Way is called the solar apex. This path points roughly toward the bright star Deneb in the constellation of Cygnus, and forms an angle of about 90 degrees with the direction of the galactic center. The Sun's orbit around the Milky Way is not a perfect circle, but more of an elongated ellipse, influenced by the pull of the spiral arms and the uneven spread of mass throughout the galaxy. As it travels, the Sun bobs gently up and down through the Galactic Plane, passing through it about 2 3/4 times during each orbit. This motion is somewhat like the oscillation of a spring moving back and forth. For many years, scientists thought these crossings might be linked to periods of mass extinction on Earth, but later studies found no clear connection. One full orbit of the Milky Way, a galactic year, takes about 240 million Earth years. Over its lifetime, the Sun has completed around 18 to 20 such galactic years, and has only covered about 1/1250th of a full revolution since humans first appeared. The Sun and its planets move around the galaxy at about 220 kilometers per second, which is roughly 490,000 miles per hour, only a tiny fraction, about 0.07% of the speed of light. Within the heliosphere, the Sun itself moves at around 84,000 kilometers per hour. At this pace, the solar system would take about 1,400 years to travel a single light year, and about 8 days to move the distance of one astronomical unit, the space between Earth and the Sun. The direction of this motion points toward the zodiacal constellation of Scorpius. Astronomers divide the Milky Way into 4 galactic quadrants. These are large circular sectors mapped using a coordinate system that places the Sun at the center. This system helps scientists describe the positions of stars, nebulae, and other galactic features relative to our solar system. The Milky Way is one of the 2 largest galaxies in our local group, the other being the majestic Andromeda Galaxy. However, astronomers are still refining their understanding of how large the Milky Way truly is. Most of its stars are found within a disk about 80,000 light-years across, and beyond this, the number of stars drops sharply. Measuring the size of a galaxy is not simple, and different methods give different answers. One common approach uses what astronomers call the D25 standard, which marks the point where the galaxy's brightness in blue light drops to a certain level. A study in 1997 by astronomer Peter Goodwin and his colleagues compared the Milky Way with 17 other spiral galaxies. Using special variable stars called Cephids to gauge distances and brightness, they estimated that our galaxy's disk stretches to about 87,400 light-years across, with a central brightness and disk thickness similar to an exponential curve. This size is smaller than that of the Andromeda Galaxy, and also slightly below the average size for other spiral galaxies. The researchers concluded that both the Milky Way and Andromeda are not enormous giants, as once thought, but rather normal, medium-sized spiral galaxies, beautiful yet typical in the vast universe. To imagine this scale more clearly, think of the solar system out to Neptune being the size of a small coin, such as a United States quarter. In that case, the Milky Way would stretch across the entire width of the continental United States, from its eastern shores to its far western edge. An older study from the year 1978 estimated a smaller size for our galaxy, about 75,000 light-years across, showing that while our cosmic home is immense beyond comprehension, it remains one of many ordinary spiral galaxies scattered through the universe. In the year 2015, scientists made a fascinating discovery. They found a ring-shaped stream of stars known as the Triangulum Andromeda Ring, or Triand Ring, which ripples both above and below the usually flat plane of our galaxy. alongside another structure called the Monoceros ring. It was first believed that these features formed from waves or oscillations in the Milky Way's vast disk. Together, they seem to wrap around our galaxy in a magnificent circle, stretching out to a diameter of at least 50 kiloparsecs, which is about 160,000 light-years. If this idea were correct, it would mean that the Milky Way's main stellar disk was far larger than scientists had thought. However, a later study in the year 2018 challenged this view. It suggested that the Monoceros ring, the A13 structure, and the Triand ring were not gentle ripples in the disk but rather collections of stars that had been thrown outward from the main body of the galaxy long ago. These scattered stars, called stellar overdensities, moved with speeds and patterns typical of those belonging to the Galactic Halo, the enormous, faint spherical region that surrounds the Milky Way. Another research project, also from 2018, brought even more surprising news. Astronomers found evidence of disk stars much farther from the galactic centre than once thought, at distances between about 26 and 31.5 kiloparsecs, or roughly 84,800 to 103,000 light-years away. This was well beyond the region where scientists had previously believed the Milky Way's disk abruptly ended, which they once placed at only about 13 to 20 kiloparsecs, or 40 to 70,000 light-years. These new findings showed that stars exist far beyond that supposed boundary, suggesting that the galaxy's disk stretches much farther into space than anyone had imagined. In the year 2020, another study looked even deeper into the structure of the Milky Way, focusing on its mysterious dark matter halo, a vast invisible cloud of unknown matter that surrounds the galaxy. Researchers estimated that this halo extends out to nearly 292 kiloparsecs, or about 952,000 light-years from the galactic centre, giving it a total diameter of roughly 584 kiloparsecs, or nearly 1,900,000 light-years. As for the Milky Way's visible disk, it was estimated to be about 1 1/3 kiloparsecs thick, or around 4,000 light-years from top to bottom. The total mass of the Milky Way has been the subject of many studies and remains a challenging mystery. Using a limit of 200 kiloparsecs to define the galaxy's size, scientists in recent years have estimated its total mass to be about 880 billion times that of the Sun. Different methods give different results. Some estimates suggest as little as 580 billion solar masses, which would make our galaxy slightly less massive than the nearby Andromeda galaxy. Back in 2009, measurements using the Very Long Baseline Array, a network of powerful radio telescopes, found stars at the outer edges of the Milky Way racing around at speeds as high as 254 kilometers per second, or about 570,000 miles per hour. Such enormous speeds suggested that the Milky Way must be far more massive than earlier thought, perhaps similar in total mass to Andromeda, with around 700 billion solar masses within about 49 kiloparsecs, or 160,000 light-years, from the centre. In 2010, further research on halo stars revealed that within 80 kiloparsecs, the enclosed mass was again about 700 billion solar masses. A later study in 2014 estimated the Milky Way's total mass at around 850 billion solar masses, roughly half that of Andromeda. More recent calculations from 2019 increased this estimate again, to about 1,290 billion solar masses. Much of this immense weight does not come from visible stars or gas, but from dark matter, a mysterious substance that cannot be seen, yet exerts a powerful gravitational pull. Models suggest that the Milky Way's dark matter halo extends far beyond 100 kiloparsecs from the centre and contains a total mass of between 1 and 1.5 trillion solar masses. Some studies from 2013 and 2014 have proposed even wider ranges, from as much as 4.5 trillion solar masses down to only 800 billion. By contrast, the combined mass of all the stars in our galaxy is only between 46 billion and 64 billion solar masses, a small fraction of the total. In addition to its stars, the Milky Way also contains enormous amounts of interstellar gas, made up of about 90% hydrogen and 10% helium by mass. About 2/3 of this hydrogen is in its atomic form, while the remaining third exists as molecular hydrogen, which forms the raw material for new stars. This gas makes up about 10 to 15% of the total mass of all the galaxy's stars, while the interstellar dust, tiny solid grains mixed with the gas, adds another 1% to the total. In March of 2019, astronomers announced that the virial mass, a special measurement of the Milky Way's total gravitational mass, was about 1,540 billion solar masses within a radius of about 39.5 kiloparsecs, or roughly 130,000 light-years. This was more than double what earlier studies had found, reinforcing the belief that about 90% of our galaxy's mass is made of dark matter. Yet, in a more recent study from September 2023, astronomers using data from the Gaia spacecraft found a drastically smaller figure, only about 206 billion solar masses, nearly 1/10 of previous estimates. This dramatic difference shows how much there still is to learn about the true size and weight of our mysterious galactic home. The Milky Way began to take shape from one or several small dense regions of matter that appeared in the universe soon after the Big Bang, which happened about 13,610 million years ago. These early clumps of matter became the birthplaces of the first ancient star groups, known as globular clusters, where the oldest surviving stars of our galaxy were born. Scientists believe that nearly half of the material that makes up the Milky Way may have originally come from other faraway galaxies. Today, many of those ancient stars and clusters form what is called the stellar halo, the vast, faint outer region that surrounds the Milky Way. Within a few billion years after those first stars appeared, the growing Milky Way had gathered enough mass to begin spinning more rapidly. Because of the law of conservation of angular momentum, which means that spinning objects tend to keep spinning, the gas that filled the early galaxy began to flatten, changing from a roughly round cloud into a large rotating disk. Later generations of stars, including our own Sun, formed inside this spiral disk, which is why most of the younger stars we see today belong to it. Since those early times, the Milky Way has continued to grow by merging with smaller galaxies and by pulling in fresh gas from the vast region around it called the Galactic Halo. Even now, our galaxy is absorbing material from several nearby dwarf galaxies, including two of its largest companions, the Large and Small Magellanic Clouds, through a long ribbon of gas known as the Magellanic Stream. Streams of incoming gas, like the fast-moving Smith Cloud, are further evidence that the Milky Way is still feeding and changing. Computer models that simulate the universe suggest that about 11 billion years ago, the Milky Way experienced a huge merger with a massive galaxy that astronomers have named the Kraken. However, evidence from the outer parts of the Milky Way, such as its total mass, rotation and chemical makeup, shows that it has not collided with any other large galaxy for roughly the last 10 billion years. This calm, stable history makes our galaxy rather unusual, since most other spiral galaxies of similar size have gone through more recent major mergers. In contrast, our nearest large neighbour, the Andromeda Galaxy, seems to have had a more turbulent past shaped by several big collisions. Modern studies show that both the Milky Way and the Andromeda Galaxy currently sit in a region of the galaxy colour magnitude diagram known as the Green Valley. This is a transitional zone between the blue cloud, which contains galaxies that are actively forming new stars, and the red sequence, which contains older galaxies where star formation has nearly stopped. Galaxies in the Green Valley are slowly running out of the gas needed to create new stars. Simulations suggest that in about 5 billion years, star formation in the Milky Way will likely fade away completely, even though a brief surge in new star birth is expected when our galaxy eventually collides with Andromeda. Observations of other galaxies similar to ours also indicate that the Milky Way is one of the brightest and reddest spiral galaxies that still produces new stars. It stands on the very edge of youth and maturity, just a little bluer than the reddest galaxies that have already stopped forming stars altogether. Near the bright stars, glowing gas and swirling dust of the Milky Way is a huge and unseen area that few can truly understand. This hidden region is known as the dark matter halo, a large and mysterious structure that stretches far beyond everything we can see in the night sky. It lies both above and below the flat part of our galaxy, surrounding not only the solar system, but the entire Milky Way itself like a gigantic invisible ball. Even though it cannot be seen, it is believed to be one of the most important parts of our galaxy, quietly shaping its future and keeping it from coming apart. Unlike the stars and clouds that fill the Milky Way's bright spiral arms, dark matter does not shine, does not take in light, and does not bounce it back. It is truly invisible. No telescope, no matter how strong, can spot it directly. Yet astronomers are sure that it exists because they can see what it does. It leaves behind clear signs through its pull of gravity, affecting how stars, groups, and even whole galaxies move through space. It is as if the universe has a hidden frame, unseen by our eyes but needed for its shape. This hidden framework made of dark matter holds the Milky Way together and gives it its form. The proof for this mysterious halo comes from how stars move. When astronomers began to study the speed of stars in different parts of galaxies during the 1970s, they saw something odd. According to the rules of physics first described by Isaac Newton centuries earlier, stars closer to the middle of a galaxy should move faster, while those farther out should move more slowly. But when scientists measured the real speeds of stars in the outer areas, they found that these stars were moving just as fast as, or even faster than, those near the middle. Something was giving extra gravity to keep them from drifting away into space. That something, though unseen, had to exist, and it was far heavier than all the visible stars combined. This finding marked the start of the modern idea of dark matter. In the Milky Way, dark matter is thought to form a huge, roughly round halo that reaches far beyond the glowing parts of the galaxy. While the bright disk of the Milky Way spans about 100,000 light-years across, the dark matter halo could stretch several 100,000 light-years from the galactic centre, maybe even farther. This means that our whole solar system, along with all the stars, star groups and clouds we can see, are floating within this gigantic unseen bubble of mass. The dark matter halo is so huge that it outweighs all the normal matter in the Milky Way. In fact, scientists think that the visible stuff, the stars, planets, gas and dust, makes up only a small part of the total mass of our galaxy. The rest, the larger part, is dark matter. This huge halo acts like a strong gravitational anchor. It stops the galaxy's outer stars from flying off into deep space and holds together the fragile spiral shape of the Milky Way. Without it, the galaxy as we know it would not exist. The thin and thick disks filled with stars of different ages would likely be torn apart by gravity, and the whole system would slowly fall apart. Instead, thanks to the dark matter halo, the Milky Way stays steady, its stars moving in smooth paths around the galactic centre. The dark matter halo covers every part of the Milky Way. It surrounds the thin disk, where young stars and clouds shine brightly. It wraps around the thicker disk, which has older and dimmer stars, and it even stretches around the star clusters that move around the galaxy's outer edges. Beyond these, it blends with the wider galactic halo that holds ancient stars and stray space material. Altogether, the dark matter halo forms a huge gravitational shell that keeps everything inside it stable, including the solar system itself. Every orbit, from the path of the Sun around the galactic centre to the movement of faraway star clusters, is shaped by its unseen pull. Scientists think that dark matter is made of strange particles, unlike anything we have yet been able to find directly. These particles do not react with light or with normal matter in the usual way. They respond only to gravity and maybe to the weak nuclear force. Because of this, dark matter does not crash into or stick together like normal matter does. It passes through stars, planets, and even our own bodies without leaving a trace. Several ideas suggest possible types for what dark matter might be. One idea involves weakly interacting massive particles, often called WIMPs. Another idea suggests axions, very light particles that might fill space like a faint invisible mist. However, despite many years of study and countless tests deep underground and in space, no one has yet directly found these strange particles. Their real nature remains one of the greatest unsolved puzzles in modern science. Even though the dark matter halo is unseen, its effects are everywhere. It controls the motions of stars in both the thin and thick disks, affects the paths of star clusters in the galactic halo, and guides the movements of small satellite galaxies that circle the Milky Way. These satellites, such as the Large and Small Magellanic Clouds, move around our galaxy under the strong pull of dark matter. The halo also makes sure that as the Sun and its planets travel through the Milky Way, moving gently above and below the galactic plane in a slow, wave-like motion that takes tens of millions of years to finish, they stay safely tied to the galaxy. Without the pull of dark matter, the solar system could drift away into the dark emptiness of deep space. Although the dark matter halo is not made of normal matter, it still affects the Milky Way's visible parts in indirect ways. Its gravity shapes the long, thin streams of stars that form when small galaxies or star clusters are torn apart by tidal forces. These star streams twist around the Milky Way like ghostly ribbons, showing the shape of the halo itself. By studying how these streams move, astronomers can map the spread of dark matter. The paths of these broken stars act like clues, revealing the unseen structure that guides their movement. Through careful measurements, scientists have found that the dark matter halo is mostly round, though it may be slightly flattened along the plane of the galaxy because of gravitational pulls from the disk. These findings help improve models of how galaxies form and grow and give important hints about the nature of dark matter. The pull of the dark matter halo reaches across every part of the Milky Way. It affects the way the galaxy spins, making stars in the outer areas move faster than expected. It helps keep the spiral arms steady over billions of years, stopping them from breaking apart. It affects how gas clouds and space clouds are spread, and how they collapse to form new stars. Even the paths of star groups and streams above and below the solar system are gently guided by the unseen mass of the halo. In a very real sense, dark matter provides the backbone of the Milky Way, the unseen structure on which all visible parts are built. If you could stand far above the galaxy, looking down at it from an impossible distance, you would see the glowing spiral disk, the thick bulge at the centre, and the faint halo of old star clusters around it. But beyond that, reaching in every direction, there would be a huge unseen ball of dark matter stretching hundreds of thousands of light years outward. This sphere would not glow or cast shadows, yet it would be there, quietly holding everything in place. The sun, the planets, the stars, and even the farthest satellites all move within its gravitational hold. This dark matter halo not only holds the Milky Way together, but also connects it to the wider universe. Similar halos surround other galaxies, forming the cosmic framework on which the large-scale structure of the universe is built. In the grand pattern of the cosmos, galaxies are not lonely islands of light, but are instead set within large networks of dark matter strands. These strands stretch across space, linking galaxies and groups together into a huge web that shapes the universe itself. The Milky Way's halo is therefore not just a local feature, but part of a cosmic pattern that reaches across billions of light years. Understanding the dark matter halo is one of the most important goals in modern astronomy and cosmology. This mysterious and invisible structure holds the key to understanding how galaxies like the Milky Way were born, how they have changed over time, and how the universe itself behaves under the pull of gravity. The shape, thickness, and size of the dark matter halo reveal clues about the earliest moments of the cosmos. Scientists believe that it formed from tiny irregularities that appeared shortly after the Big Bang, which took place nearly 14 billion years ago. Over countless ages, these tiny differences grew stronger under the force of gravity, slowly gathering gas and dust that would later form stars, planets, and galaxies. In this way, dark matter became the silent builder of the Milky Way. Without it, our galaxy might never have come together, and without our galaxy, life as we know it might not exist at all. The dark matter halo also affects the solar system, though in ways too faint to easily notice. As the Sun travels around the centre of the Milky Way, a trip that takes about 220 million years, it moves gently up and down through the thin plane of the galaxy. During this long journey, it passes through regions where the density of dark matter slightly changes. These small differences can influence the farthest edges of the solar system, especially a huge area filled with icy bodies called the Oort cloud. Some scientists think that the slow gravitational pull of dark matter may occasionally disturb these icy objects, sending a few of them tumbling toward the inner solar system, where they appear to us as comets. Though these effects are uncertain and very small, they remind us that dark matter's reach extends even into our own corner of space. Beyond the solar system, the dark matter halo also interacts with smaller galaxies that wander too close to the Milky Way. These encounters stretch out the stars of those galaxies, creating long trails across the sky known as tidal streams. These streams act as glowing scars that tell the story of how our galaxy has grown over billions of years by absorbing its smaller neighbours. The immense gravity of the halo controls this entire process, deciding how these satellite galaxies move, collide, and slowly dissolve into the Milky Way. Through countless such events, the outer regions of our galaxy have taken shape, blending together the remnants of ancient galaxies into the halo that surrounds us today. Astronomers have developed many ways to study this hidden structure. They watch how stars and globular clusters move through the galaxy, measure the bending of light from distant objects caused by gravity, and analyze the way the Milky Way's disk rotates. Each of these methods offers part of the answer, and together they reveal something astonishing. Dark matter makes up most of the galaxy's mass. Even though we cannot see it directly, the way stars move and the stability of the Milky Way itself prove that the dark matter halo is not only real, but enormous. Scientists are working to learn more about what dark matter is made of. Deep underground, detectors are waiting to catch faint flashes of light that could appear when a dark matter particle strikes an atom. Space missions and cosmic ray experiments are also searching for possible signs that dark matter particles are colliding and destroying each other. None of these searches have yet found definite proof, but each attempt brings us closer to solving one of the universe's greatest mysteries. The dark matter halo plays a vital role in holding the Milky Way together. It maintains the delicate balance of gravity that allows stars, planets, and clusters to move safely through space for billions of years. It shapes the orbits of globular clusters, directs the movement of small companion galaxies, and controls how masses spread across the galaxy. Every star that shines in our sky stays in its place because of the invisible pull of this enormous halo. If dark matter were to suddenly disappear, the results would be disastrous. The stars on the outer edges of the Milky Way would begin to drift away into the vast emptiness of space. The spiral arms would lose their structure, and the entire galaxy would start to fall apart. Clouds of gas could no longer come together to form new stars, and even the Sun and its planets would be thrown off their stable path around the galactic center. The Milky Way, as we know it, would simply vanish. Thankfully, dark matter is not going anywhere. It has been part of our galaxy since the beginning, and will remain long after the last star fades away. The beauty we see in the Milky Way, the glowing center, the spiral arms, and the billions of shining stars, is only a small part of what is really there. Beneath that visible beauty lies an unseen structure that is far larger and far more mysterious. It shows us that most of the universe is hidden from our eyes, and that our knowledge is still only a glimpse of the full truth. As the Milky Way continues its slow rotation, taking hundreds of millions of years to complete a single turn, the dark matter halo remains quiet and constant, shaping everything within it. Its gravity not only affects our galaxy, but also influences nearby ones, such as the Andromeda Galaxy, the Triangulum Galaxy, and many smaller companions. Together, their halos form a vast web of gravity that ties the galaxies of our local group together and keeps them bound across space. Studying the dark matter halo leads us to the most profound questions about existence itself. What is the universe made of? How did it begin? And why does it look the way it does? The answers to these mysteries depend on understanding this invisible material that fills the cosmos. Though it cannot be seen, dark matter defines the structure and destiny of galaxies, clusters, and possibly the entire universe. Every shining star, every orbiting planet, and every drifting galaxy moves within its powerful unseen grasp. High above and far below the solar system, beyond the reach of any telescope, the dark matter halo continues to surround us. It gives off no light, yet it holds the Milky Way together. It never collides or glows, yet it shapes the paths of stars and worlds. Though invisible, it rules everything we can see. It is the quiet force that maintains the balance of the cosmos and the unseen foundation upon which our galaxy, and perhaps all of life, depends. Around the bright, star-filled parts of the Milky Way is a vast and mysterious region called the Galactic Halo. Unlike the flat, spinning disk of the galaxy that we can see, the halo is a huge, roughly round structure that spreads far above and below the Milky Way's main body. It acts like an invisible outer layer that surrounds everything, stretching so far out that its true edge is difficult to measure. While the galactic disk is filled with stars, gas, and dust, the halo is quiet and almost empty, made up mostly of very old stars, thin clouds of hot gas, globular clusters, and a large hidden mass called dark matter. Together, these parts form one of the most mysterious and important regions of our galaxy, connecting the bright center of the Milky Way to the deep, dark space beyond it. The halo is very different from the organized flat structure of the galactic disks. In the disk, stars move in smooth, circular orbits around the center, but in the halo, their motions are random and scattered. The stars here are spread out over enormous distances, without any clear pattern or shape. The halo stretches tens of thousands of light years away from the Milky Way's central plane, and some studies suggest that its outer edge may reach nearly 300,000 light years from the galactic center. This makes it not only one of the largest parts of our galaxy, but also its final boundary, the point where the Milky Way's gravity begins to weaken and fade into the emptiness of intergalactic space. In this sense, the halo serves as the bridge between our galaxy and the vast universe beyond, marking the outer edge of the Milky Way's influence. The stars inside the galactic halo are among the oldest ever found. Astronomers classify them as population 2 stars, ancient stars that formed long before the Milky Way's thin disk and spiral arms existed. These stars contain only small amounts of elements heavier than hydrogen and helium, which means they were born at a time when the universe was still young and had not yet gone through many cycles of starbirth and supernova explosions. Because of this, studying them gives scientists clues about what the universe was like billions of years ago. Compared with the crowded regions of the galactic disk, halo stars are few and far apart. Their orbits are also very different. Instead of moving in neat circles, they follow stretched out and randomly tilted paths. This gives the halo its roughly spherical shape and its faint ghostly appearance. Interestingly, many of these halo stars did not originally belong to the Milky Way. They came from smaller galaxies that once orbited nearby but were slowly pulled apart by the Milky Way's powerful gravity. Over billions of years, our galaxy has grown by swallowing these smaller companions, absorbing their stars, gas, and dark matter into its halo. The remains of these ancient mergers can still be seen today as faint trails of stars stretching across the sky. These are the leftover streams from dwarf galaxies that were captured and destroyed. By studying the movement and chemical makeup of these stars, astronomers can piece together the Milky Way's long and complex history, revealing how it built itself from many smaller galaxies in the early universe. Each star in the halo is like a small time capsule, holding clues about events that happened billions of years before the Sun or Earth even existed. Scattered throughout this ancient region are the Milky Way's globular clusters, dense, spherical groups containing hundreds of thousands or even millions of stars bound tightly together by gravity. These clusters float far above and below the galactic plane, shining like distant islands of light in the darkness. Because their stars are so tightly bound, they can survive for billions of years, even as the galaxy around them changes. The stars inside these clusters are some of the oldest in the Milky Way, and by studying them, astronomers learn about the earlier stages of star formation and galactic history. Each cluster acts as both a glowing beacon and a valuable scientific marker, helping researchers map the structure and motion of the Milky Way on a massive scale. Besides these clusters, the halo also contains faint streams of stars, remnants of smaller galaxies and star groups that were torn apart over time by the Milky Way's gravity. These streams form long, graceful arcs that wrap around the galaxy like delicate threads. Observing them gives scientists direct evidence that the Milky Way is still growing and changing. Even today, small galaxies continue to be drawn in, their stars pulled away and added to the halo's population. These ongoing events show that the halo is not a quiet or static place, it is constantly evolving. The paths of these stellar streams also help scientists map the distribution of dark matter, since their movement is shaped by the unseen gravitational field that dark matter creates. By tracking these motions, astronomers can measure the hidden mass that fills the halo and controls much of the Milky Way's structure. The halo is not made only of stars. It also contains vast amounts of hot ionized gas, forming what astronomers call the circumgalactic medium. This gas is extremely thin, so much that it would make even the best vacuum on Earth seem dense by comparison. But it stretches across tremendous distances. Despite being so rarefied, it plays a vital role in the Milky Way's life. The gas in this region reaches temperatures of several million degrees Kelvin, making it one of the hottest components of our galaxy. It acts as both a source and a regulator of star-forming material. When large stars explode as supernovae, they send out powerful winds filled with heavy elements that escape the galactic disk and drift into the halo. There, this material mixes with the hot gas, enriching it with new elements. Over time, some of this gas cools and falls back toward the disk in a process called the galactic fountain. Through this cycle, matter is constantly exchanged between the disk and the halo, linking them in a continuous flow that renews and sustains the Milky Way. Studying the enormous layer of hot gas that surrounds the Milky Way is one of the greatest challenges in modern astronomy. This gas does not shine in visible light but gives off most of its energy in the form of extremely energetic radiation. Because of this, it cannot be seen with ordinary telescopes. Astronomers must use special instruments that detect X-rays and ultraviolet light to study it. These powerful telescopes reveal faint glows and patterns in the light called spectral lines, which help scientists trace how the gas is spread out and how it moves through space. From these delicate clues, astronomers can map the size, temperature and thickness of what is known as the Milky Way's circumgalactic medium. These studies reveal how the galaxy grows and changes over time. Far from being a still or lifeless shell, the halo is an active and essential part of the Milky Way system. It acts like a vast recycling centre of the cosmos, linking the birth and death of stars, controlling the movement of gas and dust, and balancing the exchange of matter and energy between our galaxy and the immense emptiness of intergalactic space. Yet, the most mysterious and important part of the halo is something that no telescope can see at all: dark matter. This strange and invisible material does not give off or absorb any kind of light, but it is believed to make up most of the halo's total weight. It forms a huge, roughly spherical cloud that wraps around the entire Milky Way, enclosing everything inside: the bright disks, the stars, the clusters, and even the thin gas that fills the spaces between them. The pull of its gravity is what holds the galaxy together. Observations have shown that stars near the edges of the Milky Way move much faster than they should if only visible matter were present. The only way to explain these high speeds is to accept that there must be an enormous amount of unseen matter producing extra gravity. Without this dark matter, the stars and gas would slowly drift away into space, and the Milky Way would lose its shape. Though we cannot see dark matter directly, it acts as the hidden framework of the galaxy, shaping its form, guiding its movement, and keeping it stable across billions of years. The galactic halo extends far beyond the Sun and the solar system, stretching out in every direction above and below the galactic plane. In this vast region, stars are extremely rare. The nearest halo stars may be thousands of light years apart, leaving immense stretches of what appears to be empty space. But this emptiness is not truly empty. It is filled with invisible energy and delicate structures. Streams of ancient stars, clusters packed with hundreds of thousands of suns, clouds of superheated gas, and great amounts of dark matter all move and interact within it. These slow and subtle interactions influence how stars travel through the galaxy's disks, how smaller satellite galaxies move around the Milky Way, and even how the galaxy itself changes over time. Although the halo is faint and hard to observe, its effects can be felt everywhere. It quietly shapes the motion, the structure, and the future of the entire galaxy. As we move from the dense inner disk of the Milky Way to its more spread out thick disk, and finally to the thin and almost empty halo, we can see how complex and layered our galaxy truly is. From the crowded star-filled centre to the distant reaches of the halo, the Milky Way forms one enormous structure that stretches far beyond what the human eye can see. Our solar system lies within the thin disk, which is just a small part of this grand system. Although we live in one of the brighter and flatter regions, we are surrounded on every side by the invisible vastness of the halo, which extends far above and below us into deep space. One of the most fascinating things about the halo is that it holds several smaller galaxies within it. These are called satellite galaxies, and they orbit the Milky Way like distant companions. Among the best known are the Sagittarius Dwarf galaxy and the Large and Small Magellanic Clouds. These tiny galaxies follow complex paths around the Milky Way, sometimes passing close enough to be pulled by its gravity. When this happens, both the Milky Way and the smaller galaxies are stretched and distorted, forming long trails of stars known as tidal streams. Over time, the smaller galaxies lose some of their material, which becomes part of the halo, feeding it with fresh gas and stars. These ongoing interactions show that the halo is not a leftover from the distant past. It is still alive and changing, shaped by the constant motion of galaxies and the invisible pull of gravity. Even our solar system feels the influence of the halo, though in subtle ways. As the Sun and its planets orbit the centre of the Milky Way, they slowly rise above and dip below the galactic plane, sometimes getting closer to the halo and sometimes moving farther away. Although the halo's gas and stars are far too thin to affect our daily lives, its gravity reaches across the galaxy. It helps keep the smaller satellite galaxies in orbit, affects the movement of globular clusters, and even shapes the faraway region of the Oort cloud, where countless comets drift in the outermost part of our solar system. The immense mass of the halo keeps all of these systems tied together, making sure that the Milky Way remains whole and that stars like our Sun do not drift away into the void. The galactic halo is in many ways the great cosmic container that holds the Milky Way. It stretches far beyond the glowing spiral arms and includes every part of the galaxy: the disks, the clusters, the smaller galaxies, and the thin streams of stars that circle within it. It is made up of ancient stars, glowing clusters, scorching gas, unseen dark matter, and the faint traces of collisions and mergers from ages long past. Each of these pieces tells part of the Milky Way's long and continuing story. The oldest stars remember the galaxy's beginnings. The gas that flows through the halo and back into the disks fuels the birth of new stars. The dark matter keeps everything bound together. When seen as a whole, the halo reveals that our galaxy is not still or unchanging. It is alive, constantly growing, and connected to the larger universe around it. Studying the halo gives astronomers a rare three-dimensional view of the Milky Way. It helps them understand how all the visible parts, the stars, the clusters, and the shining spiral arms, fit within a far greater and mostly unseen structure. The halo stretches far beyond the reach of ordinary telescopes, reminding us that the Milky Way we see with our eyes is only a small fraction of what truly exists. What looks like a narrow, flat band of light in the sky is, in truth, part of an enormous spherical system that surrounds our solar system completely. The galactic halo serves as a living record of the Milky Way's history and a guide to its future. Its ancient stars tell us how the galaxy was born. Its streams trace the paths of galaxies that once orbited close by. Its hot gas regulates the ongoing cycle of stellar life and death, and its dark matter binds the entire structure together. It is both the memory and the backbone of the Milky Way, the invisible architecture upon which everything else depends. While we live within the bright and crowded disk, it is the halo that defines the true size, shape, and greatness of our galactic home. Every motion of the Milky Way, its slow rotation, its pull of gravity, its changes over billions of years, is guided by this vast and unseen sphere. The halo is not just an outer layer, it is a vital part of what the galaxy is. It connects the oldest stars with the newest, links the visible world to the invisible, and ties the local region of space to the endless depths beyond. Through it, we can finally see that the Milky Way is not a flat spiral of stars, but a rich, multi-layered, and interconnected system reaching deep into intergalactic space. And so, even though our solar system moves quietly within the thin disk, it remains part of this immense structure, connected to ancient stars above and below, held by the gravity of unseen matter and surrounded by the faint radiance of the Milky Way's invisible halo. It is through the study of this mysterious and far-reaching realm that we begin to understand the true nature of our galaxy, not simply as a cluster of stars and planets, but as a living cosmic organism, bound together through space and time by the vast and invisible power of the galactic halo. Far beyond the relatively thin disk of the Milky Way, which holds most of its young and middle-aged stars, lies a realm filled with some of the oldest and most mysterious objects in the galaxy. These ancient formations are called globular clusters. Each one is a massive, nearly spherical group of stars held tightly together by gravity. A single globular cluster can contain anywhere from a few 100,000 to several million stars, entire suns gathered into a compact, brilliant sphere. These clusters have existed for billions of years, surviving from a time long before the Earth or even the Sun was born. Inside a globular cluster, stars are packed together far more closely than anywhere near our own Sun. In the region around the solar system, stars are usually separated by several light-years of empty space. But in the crowded cores of globular clusters, the distance between stars can be only a tiny fraction of a light-year. That means thousands of stars can fit into the same volume of space that, in our local area, might hold only one. This extreme concentration of matter gives globular clusters a powerful gravitational pull, allowing them to remain tightly bound and to shine with an intense golden glow that makes them stand out even across vast cosmic distances. Because they are roughly spherical, these clusters do not lie within the flat plane of the Milky Way's disk. Instead, they travel in long, looping orbits through the galaxy's halo, a wide, faint region that stretches tens of thousands of light-years above and below the galactic plane. Seen from afar, the system of globular clusters looks like a vast three-dimensional framework surrounding the Milky Way, almost like a luminous shell made of countless shining points. This great structure has endured for more than 10 billion years, making it one of the oldest and most enduring parts of our galaxy. From Earth, a globular cluster appears as a small bright orb of light suspended in the dark sky. Through a telescope, it resembles a glittering ball made up of thousands of tiny stars packed so tightly that their light blends together. What we see is not the glow of a single star, but the combined brilliance of hundreds of thousands of ancient suns, each one quietly burning in the cold depths of space. These clusters are not only stunning to look at, but also extremely valuable for science, as they hold vital clues about how the early universe once was. Most of the stars within the Milky Way's globular clusters were born soon after the galaxy itself began to form. This makes them some of the oldest stars known to exist. They're generally small and long-lived, made mostly of simple elements such as hydrogen and helium, with only tiny traces of heavier materials like carbon, oxygen, and iron. Astronomers call them metal-poor stars, since in astronomy the word metals refers to any element heavier than helium. The lack of these heavier elements shows that the stars in globular clusters formed before the first generations of supernova explosions had filled the galaxy with the byproducts of nuclear fusion. This chemical purity makes globular clusters natural laboratories for studying the early universe. Because their stars were created from the original gas clouds that existed shortly after the Big Bang, they preserve the conditions of that ancient era. By studying the light from these stars, astronomers can learn what the Milky Way's earliest interstellar gas was like, and how star formation worked when the universe was still very young. In this way, globular clusters act as cosmic time capsules, containing frozen evidence of a period when the first stable structures were forming out of the chaos of creation. Although the stars inside these clusters are incredibly old, most of them still shine today. Because they are generally small, they burn their nuclear fuel slowly, allowing them to live for billions upon billions of years. Many have become red giants, large glowing stars nearing the end of their lives. Others have reached what astronomers call the horizontal branch phase, where they burn helium in their cores after using up their hydrogen. Some of the oldest stars have already become white dwarfs, small and dense stellar remnants that gradually cool over time. Yet, despite all these changes, the globular clusters themselves remain intact. Their strong gravitational bonds hold them together, preserving their compact, shining beauty for unimaginable spans of time, silent witnesses to the ancient history of our galaxy. Globular clusters are not spread evenly throughout the Milky Way. They do not belong to the thin disk, which contains most of the young stars and star-forming areas, nor to the thicker disk, which is filled with older but still rotating stars. Instead, globular clusters belong to the Galactic Halo, a huge round region that stretches tens of thousands of light-years beyond the Galactic Plane. Some of these clusters are fairly close to the solar system, lying only a few thousand light-years away, while others move around at distances of more than 100,000 light-years, marking the faint outer edges of the galaxy's gravitational pull. The paths of globular clusters are usually stretched rather than circular, and they are often tilted at sharp angles compared to the galactic plane. This explains why, when astronomers map their positions, the clusters appear as scattered points of light above and below the disk, lonely groups of stars drifting through the halo. Their spread forms a kind of unseen framework that outlines the Milky Way's gravitational shape. By carefully studying their movements, astronomers can estimate the total mass of the galaxy, including the mysterious dark matter that makes up most of its pull but gives off no light. The stars that fill globular clusters belong mostly to what astronomers call Population 2, a label that refers to their low metal content and great age. These stars formed from gas clouds made almost entirely of hydrogen and helium, the simplest and most common elements in the universe. In contrast, younger stars in the thin disk of the Milky Way, including the Sun, belong to Population 1, meaning that they have much higher amounts of heavier elements. The difference in chemical makeup affects many parts of a star's behavior, including its color, temperature, and how fast it changes over time. Population 2 stars tend to be slightly bluer and less bright than metal-rich stars of the same size, and they change more slowly, allowing them to last for enormous stretches of cosmic time. Because globular clusters are so tightly packed, they create an environment very different from that of ordinary star neighbourhoods. The gravitational pulls among the stars are strong, and close encounters happen often. Over time, these interactions can cause many kinds of changes. Some stars may trade energy, making their paths within the cluster shift. In rare cases, two stars may crash or join together, forming a single, heavier star. Double star systems, pairs of stars moving around each other, are especially common in globular clusters, and meetings between doubles and single stars can lead to complex exchanges of energy and motion. These internal movements can slowly change the shape of a cluster over billions of years, a process known as dynamical evolution. The densest areas tend to lose energy as stars trade motion, leading to an effect called core collapse, in which the center becomes even denser. Meanwhile, some stars gain enough energy from these meetings to leave the cluster completely, drifting into the halo as lone wanderers. Despite this constant motion inside, the cluster as a whole stays held together by gravity and remains surprisingly stable, with its overall shape lasting through cosmic time. The crowded environments of globular clusters also give rise to strange and rare types of stars that are hardly ever seen elsewhere. One example is the blue straggler, a star that looks unexpectedly young and bright compared to the surrounding stars. Blue stragglers are thought to form when two stars join together, or when one star in a pair transfers mass to its partner, making it look young again. Another example is the millisecond pulsar, a fast-spinning neutron star with a strong magnetic field that sends out regular flashes of radiation. Such objects act like extremely accurate cosmic clocks, and when found in globular clusters, they allow astronomers to study the gravitational and magnetic conditions inside these dense systems. Variable stars, whose brightness changes over time, are also common, and have long been used to measure distances to the clusters and to set the scale of cosmic distances. In this way, globular clusters are not just still remains but living laboratories where star life, motion, and strange physics can all be studied together. They show how gravity shapes star systems on both small and large scales, and how the interactions between stars can affect their individual and shared paths. Globular clusters also provide key clues about the history of the Milky Way itself. Not all of them were born inside our galaxy. Astronomers have found that some clusters were likely taken from smaller satellite galaxies that merged with or were absorbed by the Milky Way billions of years ago. These captured clusters can be recognized by their chemical makeup and paths, which differ from those of clusters that formed naturally within the Milky Way. In this way, globular clusters act as fossils of galactic growth, keeping within their stars the traces of ancient crashes and mergers. By studying their positions and movements, scientists can rebuild the step-by-step process by which the Milky Way grew to its current size, through the slow gathering of smaller systems over cosmic time. Clusters that now move far above and below the galactic plane may once have belonged to tiny galaxies that were pulled in by the Milky Way's gravity. Their stars and clusters were torn away and added to the halo, leaving behind faint trails that still show the paths of those long-gone systems. Because globular clusters live in the relatively calm region of the halo, far from the disturbing gravitational effects of the galactic disk, they have lasted with their structure mostly unchanged for more than 10 billion years. This makes them unique witnesses to the earliest times of the galaxy's birth. Their steadiness and long life mean that they can still tell astronomers what the Milky Way was like when it was young, before the spiral arms formed and before most of its stars were born. From an observational point of view, globular clusters are among the most noticeable and easily recognized objects in the night sky. Even small telescopes can show some of the closer clusters as dense round patches of light, while larger telescopes or space observatories can show them as thousands of individual stars. When seen in detail, a typical cluster shows a bright center, surrounded by a slowly thinning group of stars, fading smoothly into the darkness of space. For the nearest clusters, such as Omega Centauri or Messier 13, individual stars can be clearly seen, and their properties measured with great accuracy. More distant clusters, however, look like smooth, glowing balls whose light comes from the combined glow of countless stars. Astronomers have listed and studied hundreds of globular clusters, both inside the Milky Way and in nearby galaxies, finding their distances, ages, and metal content. These measurements are important for testing ideas about how stars change and for setting the full timeline of galactic history. Above and below the solar system, Globular clusters form a vast vertical network that outlines the shape of the galactic halo. Their spread stands out sharply against the flat, smooth layer of stars in the thin and thick disks. The halo's sparse population means that each cluster stands out clearly against the dark background of space, acting as a bright marker of the Milky Way's wide structure. Beyond their role in our own galaxy, globular clusters are deeply important for the study of the universe as a whole. Because they contain some of the oldest known stars, measuring their ages gives a lower limit for the age of the Milky Way and even for the universe itself. The oldest clusters have been dated to more than 12 billion years, showing that they formed not long after the universe's first billion years had passed. In this way, globular clusters act as timekeepers of cosmic history. Their internal movements also show information about the invisible matter that fills galaxies. By studying the speeds of stars inside a cluster, astronomers can estimate its total mass and see how tightly it is held by gravity. When the movements of many clusters throughout the halo are combined, the results can be used to map the Milky Way's gravitational field and to guess the spread of dark matter. Thus, studying these ancient star systems helps us understand one of the universe's greatest mysteries. The long survival of globular clusters over billions of years shows the careful balance between gravity, star changes, and galactic movement. While individual stars in the Milky Way are always being born and dying, and while spiral arms shift and gas clouds drift through the disk, the clusters remain firm, compact, stable, and lasting. They represent the oldest surviving witnesses of the galaxy's growth and change, keeping the memory of a time when the Milky Way was still collecting its mass from the surrounding universe. Each cluster above and below the solar system shines as a leftover from that faraway past, a cosmic light that shows the long story of star birth, life, and death. The ancient stars inside these clusters stand in clear contrast to the young, bright stars that fill the thin disk, where new stars continue to form within gas clouds. They also differ from the older, more spread-out stars of the thick disk that surround the Galactic Plane. Together, these different parts, the thin disk, the thick disk, and the halo of globular clusters, show the vertical complexity of the Milky Way, revealing it not as a flat, simple structure, but as a layered and changing system with deep historical roots. By studying globular clusters, astronomers gain understanding of the Milky Way's beginning, its long-term changes, and the universal forces that control the behavior of stars and galaxies. These ancient, tightly bound spheres provide proof of the earliest star formation, of the build-up of chemical elements over time, and of the interactions that have shaped the galaxy's size and structure. As we move farther away from the solar system and rise above the flat plane of the Milky Way, we pass through many strange and beautiful regions. We leave behind the outer edges of the galactic halo, the dense swarms of ancient globular clusters, the fast-moving clouds of gas, and the small companion galaxies that orbit our own. Eventually, we reach a truly remarkable point, the boundary where our galaxy ends and the vast realm of intergalactic space begins. Inside the Milky Way, space is lively and full. Stars shine in great numbers, glowing clouds of gas and dust drift and mix. Dark matter pulls on everything with invisible force, and streams of energetic particles called cosmic rays race about at nearly the speed of light. But beyond the edge of our galaxy, everything changes. The universe opens up into an immense, silent void, where matter becomes so thin that even finding a single atom in a cubic meter of space is considered relatively dense. Leaving the Milky Way is like stepping out of a crowded, bright city and entering an endless, quiet desert, but on a scale so enormous that the human mind can barely begin to grasp it. Yet even this incredible emptiness is not completely empty. Intergalactic space still holds a faint mist of gas, mostly hydrogen and helium, the very same elements that filled the newborn universe shortly after the Big Bang. This gas is spread so thin that it cannot be seen with the naked eye, but it stretches across billions of light years, forming delicate filaments that connect galaxies like threads in a vast web. These ghostly filaments make up what scientists call the cosmic web, the immense structure that binds together galaxies, clusters, and superclusters across the universe. The temperatures in this lonely space vary greatly. Some areas close to galaxies remain relatively cool, while others are heated to astonishing levels by violent galaxy collisions or the crushing pull of massive cosmic structures. Every now and then, a thin cloud of gas or a tiny grain of dust drifts through this emptiness, but such traces are extremely rare. Even the outermost edges of the Milky Way's halo contain far more matter than most regions of intergalactic space. Invisible yet powerful, dark matter also fills this emptiness, weaving through intergalactic space like unseen scaffolding. Though we cannot see it directly, its gravity shapes the motion of galaxies and the very structure of the universe. The Milky Way, surrounded by its own dark matter halo, sits within a huge network of these invisible filaments that hold galaxies together in groups, clusters, and superclusters. Even where there seems to be nothing at all, dark matter continues to influence the paths of drifting galaxies, guide the flow of intergalactic gas, and form the framework upon which the entire universe is built. Beyond the reach of our galaxy's gravity and magnetic field, the pull of other galaxies begins to take over. Here, the familiar boundaries of the Milky Way give way to a grander scale, one ruled by the slow, majestic interactions between galaxies spread across immense cosmic distances. Intergalactic space is also filled with a constant background of radiation and high-energy particles that have been travelling across the universe for billions of years. Cosmic rays that escape from galaxies like ours continue on their long journeys through these vast spaces, while faint photons from the cosmic microwave background, the oldest light in existence, spread evenly through all of intergalactic space. This ancient light carries memories from the universe's earliest moments, only a few 100,000 years after the Big Bang. The radiation out here is calm and uniform, unlike the energetic environment within galaxies. It forms a gentle background glow against which galaxies drift and evolve through time. By studying this quiet emptiness, astronomers learn about the universe on its grandest scale. How galaxies are born, how matter spreads, and how energy moves through the cosmos. The incredible emptiness of intergalactic space also reveals the true vastness of the universe. The distances between galaxies stretch across millions of light years, while the gaps between galaxy clusters can span tens of millions of light years. Compared to this, the Milky Way, with all its bright stars, colourful nebulae and swirling clouds, seems almost small and crowded. Yet even in this endless void, matter is not spread out perfectly evenly. Tiny irregularities in the early universe, faint differences in density that were once almost invisible, slowly grew under the pull of gravity. Over billions of years, these slight differences drew matter together into the filaments and clusters we see today, while leaving immense empty regions in between. To leave the Milky Way, then, is to travel from a rich and crowded environment into a silent, thinly populated sea of space, where galaxies shine like distant islands of light scattered through an ocean of darkness. One of the most fascinating features of intergalactic space is that it is not truly disconnected. Even in regions that seem completely empty, faint streams of gas, dark matter, and weak magnetic fields link galaxies across unimaginable distances. These filaments, which form the cosmic web, are like the invisible framework of the universe, connecting our Milky Way to its neighbours, the Andromeda Galaxy, the Triangulum Galaxy, and countless others beyond the local group. These hidden connections shape how galaxies grow, interact, and evolve through the ages. Intergalactic space is not just a passive void, it is an active, living network through which gravity, matter, and energy flow, holding the entire universe together as one vast, interconnected whole. This immense emptiness also offers astronomers a precious opportunity. Because there is almost no matter to block or distort light, the glow from distant galaxies can travel for billions of years before reaching us, nearly unchanged. Through this light, scientists can look back into the deep past and witness galaxies as they appeared billions of years ago, learning about the history of the universe, the expansion of space, and the way cosmic structures have evolved over time. By studying the faint space above and below our galaxy, far beyond its halo and its small companion galaxies, we can understand how the Milky Way fits into the great cosmic web, how it interacts with its nearest neighbours, and how the universe itself continues to grow and change across the ages. From the viewpoint of our solar system, completely leaving the Milky Way and entering intergalactic space would mark one of the greatest and most dramatic changes imaginable. As we moved farther away, all the familiar parts of our galaxy would slowly fade from sight. The thin and thick disks filled with stars, the swirling clouds of gas and dust where new suns are born, the ancient globular clusters shining like golden spheres, and the small companion galaxies that orbit the Milky Way. Soon, the solar system would find itself drifting through a vast and almost empty region of space. This enormous expanse would seem quiet and desolate, filled mostly with thin traces of gas spread across unimaginable distances. Yet even here, space would not be truly empty. Invisible threads of dark matter would stretch across the void like a hidden framework, linking faraway galaxies together. Faint glows of radiation, the lingering light from countless distant galaxies, would still reach us across billions of light years. Although this intergalactic space might appear still and lifeless, it is never truly at rest. Gravity continues to pull on everything, slowly shaping the paths of galaxies and the motion of the unseen dark matter. The energy of ancient cosmic events and the slow drifting of entire galaxy clusters keep this seemingly empty realm alive with subtle motion. Even in the lonelier stretches between galaxies, the universe remains connected, constantly changing, evolving, and reminding us that every corner of the cosmos is part of one vast living system. Cosmic rays are streams of incredibly fast and energetic particles that move through space at nearly the speed of light. Most of them are simple protons, but some are heavier atomic nuclei, electrons, or even antimatter versions of electrons called positrons. Though they cannot be seen by the human eye, they are everywhere, constantly passing through the solar system from all directions. Their endless flow shows just how active and energetic our galaxy truly is. These cosmic travelers come from many different and violent events across the universe. Within our own Milky Way, most cosmic rays are thought to be created by the explosive deaths of giant stars, called supernovae. When such a star explodes, it sends out powerful shockwaves that speed up nearby particles to almost the speed of the light, turning ordinary bits of matter into high-energy wanderers of space. But not all cosmic rays come from inside our galaxy. Some begin their journey in faraway galaxies, especially around the extremely bright and energetic centers known as active galactic nuclei. Others are born in sudden flashes of gamma-ray bursts, brief but unbelievably powerful explosions that can shine brighter than an entire galaxy for a few short moments. These particles then travel for millions or even billions of light years before reaching the Milky Way, carrying with them clues about the extreme events that created them. Once cosmic rays enter our galaxy, their paths become very complicated. They are constantly influenced by the Milky Way's magnetic fields, which twist and bend their movement, sending them on tangled and unpredictable routes. These magnetic fields guide the rays through all parts of the galaxy, across the thin disk where most stars lie, through the thicker disk made of older stars, and out into the huge halo that surrounds everything. As they travel, the cosmic rays collide with clouds of gas and dust, ionizing atoms and slightly changing the chemistry and temperature of the interstellar environment. In dense molecular clouds, this ionization sparks slow chemical reactions that help form complex organic molecules, which can later take part in the creation of new stars. Cosmic rays, though invisible, play a quiet yet essential role in star formation. By altering how gases are ionized, they affect the way magnetic fields interact with interstellar clouds. This influences how gas heats up and cools down, and can even help trigger the collapse of dense cloud regions where new stars begin to form. In this way, cosmic rays act as a link between violent cosmic explosions and the peaceful birth of stars, connecting the most energetic events in the universe to the creation of new worlds. Their strength, however, is not the same everywhere. The number of cosmic rays reaching different places depends on where you are in the galaxy, how much shielding there is, and even on the activity of the Sun. The Sun's solar wind creates a vast bubble called the heliosphere, which acts as a magnetic shield around the solar system. This bubble deflects many cosmic rays and keeps most of them from reaching Earth. Yet, when the Sun becomes quiet, during times of low activity, the shield weakens, and more of the most energetic cosmic rays manage to pass through and reach our planet. Far beyond the solar system, in the Galactic Halo, cosmic rays move more freely. There, they encounter fewer obstacles and can travel immense distances across space. Astronomers use this to study the Milky Way's hidden magnetic fields by tracking how these charged particles are deflected. This helps reveal the shape, strength, and turbulence of the invisible magnetic web that surrounds the galaxy. As cosmic rays move through the halo, they also interact with the hot gas found there, depositing energy and subtly affecting the temperature and motion of this mysterious outer region. Cosmic rays are also responsible for creating new forms of radiation. When they hit atoms in the interstellar medium, they generate gamma rays, powerful bursts of energy that can be detected by telescopes in space. This gamma ray glow helps astronomers map where cosmic rays are most common and shows the regions where particles are being accelerated. In this way, cosmic rays act as messengers, carrying information from distant and hidden events, connecting what happens in the galactic disk to what lies far out in the halo and beyond. They also reveal parts of the universe that normal light cannot show. By studying where cosmic rays come from, how much energy they have, and what they are made of, scientists can learn more about the Milky Way's magnetic structure, the nature of interstellar space, and even how dark matter might be spread throughout the galaxy. These particles trace the invisible framework of our cosmic home, proving that space is not empty, but filled with unseen motion and energy, connecting distant stars and galaxies with our local environment. Even the solar system and Earth are constantly touched by these cosmic visitors. When they strike planetary atmospheres, they contribute to background radiation, influence atmospheric chemistry, and over the course of millions of years may even have affected the evolution of life. On Earth, when cosmic rays hit the upper atmosphere, they create showers of secondary particles such as neutrons and muons. These can be detected at the surface or even deep underground. By studying these interactions, scientists not only learn about the behavior of the universe, but also gain insights into climate processes, biological effects of radiation, and the risks faced by astronauts in space. At their core, cosmic rays are streams of extremely energetic particles that move at speeds close to that of light, constantly passing through the regions above and below the solar system and spreading through every part of the galaxy. They come from the final explosions of giant stars, from pulsars, and from faraway galaxies, affecting the makeup, temperature, and motion of the gas and dust between stars. By charging gas, interacting with thick clouds of molecules, and creating gamma rays, cosmic rays help decide where and how new stars are born, shape the galaxy's outer regions, and reveal processes that would otherwise stay hidden. Space above and below our solar system is far from empty. It is filled with these energetic particles that link the most powerful cosmic events to the ongoing activity and growth of the Milky Way, showing that our galaxy is full of movement, connection, and hidden energy. This wider view shows that cosmic rays are not just particles flying through space. They form a link between the violent deaths of stars, the gentle chemistry of molecular clouds, the patterns of the galaxy's magnetic fields, and even the surroundings of our own solar system. They represent the living pulse of the Milky Way, proving that every part of space, from the crowded star-filled disk to the thin outer halo and beyond, is part of one vast, energetic and connected galactic system. The Milky Way galaxy is far from being an empty, silent void. Instead, it is filled with immense clouds of gas and fine dust, materials that serve as the building blocks of everything we know, stars, planets, and even life itself. When we look up at the night sky, many of these regions may seem completely dark and empty, yet they are full of hidden activity. These vast areas form what astronomers call the Interstellar Medium, often shortened to ISM. The interstellar medium is the collective term for all the gas, dust, and tiny particles that drift through the space between stars within a galaxy. It is mainly made of hydrogen and helium, the two simplest and most common elements in the universe, along with smaller amounts of heavier elements such as carbon, oxygen, nitrogen, and silicon. Although the interstellar medium is incredibly thin, much thinner than the air we breathe, it fills such a gigantic volume that it contains enough material to create billions of stars during the lifetime of the Milky Way. To give an idea of how thin it is, in many areas of interstellar space there are fewer than 1 atom per cubic centimetre, while the same volume of air on Earth contains about 10 billion molecules. But because the Milky Way stretches across more than 100,000 light-years, even this extremely sparse matter adds up to an enormous total mass. The interstellar medium can be thought of as the connective web of the galaxy. It links stars, nebulae, and planetary systems in a continuous cycle of creation, destruction, and renewal. When stars reach the end of their lives, they throw off their outer layers or explode as supernovae, releasing gas, dust, and heavier elements into space. This material mixes with the surrounding medium, becoming the raw material for new generations of stars and planets. Over time, gravity, magnetic fields, and radiation from nearby stars act together to compress parts of this gas and dust, causing them to form new stellar systems. In this way, the interstellar medium is essential for the long-term evolution of the Milky Way, recycling matter over billions of years and ensuring that the galaxy remains active and alive. Different layers of the interstellar medium exist above and below the Milky Way's central plane, each with distinct densities, temperatures, and chemical compositions. Near the Galactic Plane, where our solar system is located, the gas and dust are denser and more dynamic. This region, known as the thin disk, stretches a few hundred light-years above and below the galaxy's midplane. Within it, thick clouds of gas and dust constantly interact with radiation and magnetic forces. These are the places where most of the Milky Way's ongoing star formation happens. Beyond this lies the thick disk, which extends farther from the galactic plane. Here, the material becomes much more diffuse, and star formation is rarer, though gas and dust still linger as silent reminders of earlier eras in the galaxy's history. Hydrogen, the simplest and most abundant element in the universe, makes up most of the interstellar gas. It appears in two main forms: neutral atomic hydrogen, written as Hi, and molecular hydrogen, written as H2. The atomic form creates vast, thin clouds that can stretch over thousands of light-years. These clouds are especially valuable to astronomers because they emit a faint radio signal at a wavelength of 21 centimeters, produced by a subtle change in the orientation of the hydrogen atom's electron. This signal allows scientists to map the Milky Way's structure, even in regions hidden behind thick clouds of dust. With radio telescopes, they can trace the galaxy's spiral arms and measure how the gas moves under gravity, revealing how the Milky Way spins and how its mass is distributed. Molecular hydrogen, on the other hand, is found in much colder and denser places known as molecular clouds. These are the true nurseries of stars. Inside them, temperatures can drop to only a few tens of degrees above absolute zero, cold enough for hydrogen atoms to pair up into H2 molecules. As the gas cools, it becomes easier for gravity to pull it together. When a region inside a molecular cloud grows dense enough, gravity overcomes internal pressure and the cloud begins to collapse. This process gradually leads to the birth of one or more protostars, which are surrounded by spinning disks of gas and dust. Over time, these disks can evolve into complete planetary systems. One of the most famous examples of such a stellar nursery is the Orion Nebula, located within the thin disk of the galaxy above our solar system. There, new stars are actively forming, just as they do in countless other regions scattered across the Milky Way. Helium, the second most abundant element in the universe, also forms a major part of the interstellar medium. Although helium rarely combines with other elements, it adds significantly to the total mass and helps regulate the temperature of interstellar gas. Alongside hydrogen and helium, trace amounts of heavier elements, collectively called metals by astronomers, are also present. These include carbon, nitrogen, oxygen, silicon, iron, and others. Such elements are produced deep inside stars through nuclear fusion and are spread throughout the galaxy when those stars die. This enrichment process makes the interstellar medium more complex over time, allowing the formation of new and more intricate molecules. Some of these molecules are the same kinds that form the foundation of life on Earth. Scientists have detected organic compounds such as formaldehyde, methanol, and even simple amino acid precursors drifting in interstellar clouds. Their presence suggests that the basic ingredients for life are not limited to our planet, but are scattered widely across the Milky Way, waiting for the right conditions to come together once again and create new worlds. The dust part of the interstellar medium is made up of tiny solid particles, often smaller than 1 micrometer in size. These grains are made mostly of silicates, carbon-based materials, and different kinds of ices that form under very cold conditions. Dust plays several important roles in how the galaxy changes over time. First, it provides surfaces where chemical reactions can happen, allowing simple atoms to join together into more complex molecules. Second, dust helps cool dense areas of gas by giving off infrared light, a process that allows gravity to pull matter together more easily during star formation. Third, dust changes the way light travels through the galaxy. It absorbs and scatters starlight, causing effects such as dimming and reddening. When starlight passes through dusty areas, shorter wavelengths, like blue light, are scattered more strongly than longer ones, making the stars look redder than they really are. This effect gives astronomers clues about how much dust there is and how it is spread along the line of sight. dust is also the cause of the dark nebulae seen in space pictures, where thick collections of particles block the light of stars behind them. These features can be seen both above and below the galactic plane, and are especially common along the spiral arms where dense molecular clouds exist. When lit by nearby stars, these clouds create reflection nebulae, where light is scattered instead of absorbed, giving them a blue tint. In some cases, ultraviolet light from hot young stars removes electrons from the nearby gas, creating emission nebulae that shine in bright colours depending on their chemical makeup. For example, hydrogen gives off red light in the well-known H-alpha line, while oxygen can produce greenish or bluish colours. Such nebulae show areas of recent star formation and help scientists understand the physical conditions of the interstellar medium. The interstellar medium is not the same everywhere, but divided into several phases, each with different temperatures, densities, and levels of ionization. The cold neutral medium, made of atomic hydrogen at temperatures of a few dozen kelvins, exists together with the warm neutral medium at several thousand kelvins. There are also warm ionized areas, mainly around young hot stars, where ultraviolet light has knocked electrons off atoms. In addition, the hot ionized medium, created by supernova explosions, can reach millions of degrees. The interaction between these phases makes a constantly changing environment. Shock waves from supernova, stellar winds from massive stars, and the rotation of the galaxy all stir and mix the gas. Over time, material moves between phases, cooling, heating, clumping, or spreading as the galaxy changes. Above the galactic plane, inside the thin disk, interstellar clouds are fairly dense and often gathered along the spiral arms. These are areas where the galaxy's spiral pattern squeezes gas and dust, helping new stars to form. Huge molecular clouds in these areas can stretch for hundreds of light years and have enough mass to create tens of thousands of stars over millions of years. Inside these large clouds, smaller star-forming regions appear where turbulence and gravity make pockets of gas collapse. Once massive stars form, their strong radiation, stellar winds, and later supernova explosions send energy back into the surrounding medium. This energy both breaks up existing clouds and starts new collapses in other places, creating a cycle that drives the long-term changes of the galactic disk. Below the galactic plane, in the thicker disk, things are different. The gas and dust there are more spread out and less active in making new stars. These areas are mostly made of older material, leftovers from earlier stages of the galaxy's history. The chemical makeup of the thick disk usually shows fewer heavy elements, meaning that the gas has been less enriched by later generations of stars. Over billions of years, material from the thick disk slowly mixes with the galactic halo, a much larger and rounder part of the Milky Way. The halo contains very old stars and globular clusters, as well as hot ionized gas that may interact with matter moving in and out of the galactic disk. Through these processes, the thick disk acts as a middle zone between the dense star-forming areas near the plane and the thinner outer parts of the galaxy. Interstellar gas and dust are also closely connected to the galaxy's magnetic field and the flow of cosmic rays, very energetic particles that move through space almost at the speed of light. The magnetic field affects how charged particles move inside the interstellar medium and can shape the structure of gas clouds. At the same time, interactions between cosmic rays and interstellar matter influence the chemical and energy balance of the ISM. The solar system itself moves slowly up and down across the galactic plane over a period of about 60 million years. As it passes through areas with different density and magnetic strength, the solar system experiences changes in the flow of cosmic rays. Denser clouds may block some of this radiation, while thinner areas let more of it through. Such changes can slightly affect the radiation environment of the solar system and possibly influence the long-term conditions on Earth and other planets. Astronomers study the makeup and spread of interstellar gas and dust, using many observing methods across the electromagnetic spectrum. Radio telescopes detect the 21-centimeter line of atomic hydrogen, showing the structure of the galactic disk and its spiral arms. Infrared observatories detect light from dust grains warmed by starlight, mapping areas that are otherwise hidden in visible light. Ultraviolet and X-ray instruments study ionized gas and hot plasma, while optical telescopes capture the visible glow of emission nebulae. By combining information from all these wavelengths, scientists can build a three-dimensional picture of the Milky Way's structure. Such maps show that above and below the solar system, the spread of matter forms a layered system where dense molecular clouds Thin atomic regions and hot ionized gas exist together in a complex balance held by gravity, pressure, and energy from stars. The interstellar medium not only shapes the galaxy's structure, but also affects how planetary systems form and change. Inside molecular clouds before stars are born, many complex organic molecules can form on the surfaces of dust grains. These molecules include simple sugars, alcohols, and building blocks of amino acids. When new stars and planets form, this material becomes part of comets, asteroids, and small planetary bodies. Over time, these objects can bring organic compounds to young planets, possibly starting the chemistry that leads to life. Studies of meteorites and comets in our own solar system show chemical patterns that suggest an interstellar origin. This evidence connects the chemistry of distant clouds to the ingredients that eventually made Earth capable of supporting life. The way the Milky Way looks in the night sky is also because of the interstellar medium. The bright milky band stretching across the sky is our view through the crowded disk of the galaxy, where starlight mixes with faint light from gas and dust. When seen in infrared light, this band shows detailed patterns of dust lanes and glowing molecular clouds. Well-known nebulae, such as the Orion Nebula, the Eagle Nebula, and the Horsehead Nebula, are visible examples of the same processes happening above and below the solar system. In these regions, light from nearby stars shines on the gas around them, creating bright colours and shapes that show the structure and makeup of the interstellar medium. These nebulae are not just beautiful sights, but active places where scientists can directly watch the birth of stars. The interstellar medium also records the Milky Way's past. The amounts of elements within the gas and dust give clues about how many generations of stars have lived and died in different areas of the galaxy. By measuring these amounts, astronomers can piece together how the galaxy's chemical makeup changed over time, from the simple hydrogen and helium left after the Big Bang to the complex mix of elements we see today. The movement of gas clouds also helps trace the gravity shaping the galaxy. Differences from expected orbital speeds point to dark matter, an invisible substance that affects gravity but does not give off light. So, studying the interstellar medium helps scientists understand not only star formation, but also the deeper structure of the universe itself. Besides the internal processes, the interstellar medium also interacts with material moving in and out of the galaxy. Streams of gas can flow inward from intergalactic space, adding fresh material for star formation. At the same time, powerful events like supernovae and galactic winds can push gas out into the surrounding halo, or even beyond into intergalactic space. These inward and outward flows control the galaxy's long-term growth and keep the balance of matter and energy. The borders between the galactic disk and halo are not fixed, but are constantly reshaped by these exchanges. Above and below the solar system, especially in the far parts of the thick disk, such interactions play an important role in shaping the Milky Way's overall structure. Without the interstellar medium, the Milky Way would be a still collection of aging stars slowly fading away. Instead, the presence of gas and dust keeps a continuous cycle of renewal going. Stars are born, live, and eventually return material to the ISM, enriching it with heavier elements. This enriched material forms new stars and planets, keeping the process going without end. The solar system itself is part of this cycle, formed about 4.5 billion years ago from the collapse of a molecular cloud already mixed with material from older stars. The atoms that make up the Sun, Earth, and all living things once belonged to the interstellar medium. Even now, the solar system remains inside this vast sea of gas and dust, moving through it as the galaxy turns. Deep within the wide layers of the Milky Way, from its thin star-filled disk to the thicker, older one, and even into its faint misty outskirts, there exist enormous and mysterious regions called molecular clouds. These clouds, made of gas and dust, are among the most important and fascinating parts of our galaxy. They are the places where stars are born, the true nurseries of the cosmos. In a universe filled with dazzling light and burning suns, these clouds stand out because they are some of the darkest and coldest places known. Yet, hidden in their quiet, shadowy depths, the spark of new light begins, the first stage in the birth of a star. Molecular clouds are quite different from the thin, widespread gas that fills much of the Milky Way. The ordinary interstellar gas is made of atoms and ions scattered so far apart that it is almost a vacuum. In contrast, molecular clouds are much denser and colder. Their temperatures range between about 10 and 30 degrees above absolute zero, roughly from 10 to 30 Kelvin, or about -263 to -243 degrees Celsius. At such freezing temperatures, atoms move so slowly that they can easily stick together, forming molecules. The most common of these is molecular hydrogen, written as H2, made when two hydrogen atoms join. This simple molecule is the main ingredient for creating stars. Without it, no cloud could collapse tightly enough for nuclear fire to ignite, and no new suns would ever shine. But hydrogen is not the only substance in these cosmic nurseries. Mixed into the cold gas are tiny grains of interstellar dust and small amounts of more complex molecules, such as carbon monoxide, ammonia, and water vapor. Even more remarkable are the organic molecules found within these clouds, made of carbon, hydrogen, oxygen, and nitrogen, the same elements that form the chemistry of life itself. These compounds are not just random leftovers floating in space. They play key roles in the chemical growth of the galaxy. When new stars form, their heat and radiation reshape these materials, forging heavier elements and more complex molecules. Some of this material may later become part of planets, moons, or comets, carrying with them the seeds of life's earliest ingredients. Molecular clouds can be truly enormous. Some stretch only a few light years across, while others span hundreds of light years, holding enough gas and dust to form thousands of stars as large as our own Sun. One of the most famous examples is the Orion Molecular Cloud Complex, found just above the Milky Way's thin disk. This vast region is filled with swirling gas, glowing dust, and young stars, including the famous Orion Nebula, one of the most photographed and studied places in the night sky. In this cosmic nursery, the dark coldness of space transforms into brilliant light, showing how the quietest corners of the galaxy can give birth to blazing beauty. Inside these clouds, the gas and dust are far from evenly spread. They twist and stretch into long filaments, dense knots, and compact clumps. In the thickest parts, gravity begins to take charge, pulling material inward. As the gas and dust collapse, the growing pressure and heat at the center gradually rise. Eventually, the core becomes so hot and dense that nuclear fusion begins, the process that makes stars shine. And at that moment, in the heart of darkness, a new star is born. This birth does not happen quickly. It takes millions of years for a cloud to collapse into a shining star. In the beginning, the forming star is called a protostar, a young, still-growing sun wrapped in a thick cocoon of gas and dust. As it feeds on material from its surroundings, some of that material flattens into a spinning disk. Later, this disk may form planets, moons, and asteroids, turning a cloud into a complete solar system. When the core becomes hot enough for hydrogen to fuse into helium, the protostar becomes a true star. The powerful light and wind it releases then push away the leftover gas, carving bright, glowing shapes known as nebulae, the beautiful clouds we see shining across the galaxy. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have revealed these magnificent sights in great detail. The most breathtaking and colourful nebulae, such as the Eagle Nebula or the Carina Nebula, are actually regions of active starbirth hidden within molecular clouds. Their brilliant colours come from gas excited by the fierce ultraviolet light of newborn stars. In some parts of these clouds, the dust is so thick that even visible light cannot pass through, leaving dark patches that block the stars behind them. These dark nebulae may seem empty, but they are rich with hidden promise, concealing countless stars that are still waiting to be born. Below the main disk of the Milky Way, molecular clouds can also be found, though they are fewer and quieter than those above. The thick disk contains older stars and less gas overall, but its clouds still play a part in the galaxy's grand story. Star formation there happens more slowly, but it remains just as meaningful. These clouds hold the remnants of earlier generations of stars, material enriched with heavier elements made long ago in dying suns. Some of this gas may have drifted down from the thin disk, while some may have come from small satellite galaxies that once brushed past the Milky Way. In this way, the molecular clouds of the thick disk serve as cosmic memory keepers, preserving the story of ancient stars and linking the distant past to the living present of our galaxy. By studying the great clouds of molecules found in both the thin and thick layers of our galaxy, astronomers can trace how the Milky Way has slowly changed over time. The differences in density, temperature, and the amount of heavy elements between clouds above and below the solar system helps scientists understand why some regions give birth to large, short-lived stars, while others form smaller ones that burn gently for billions of years. These differences also shape the kinds of planets that are born. A cloud filled with heavy elements is more likely to create rocky planets like Earth, while a simpler, cleaner cloud with fewer metals may mostly form giant gas worlds or lifeless systems. Yet, these molecular clouds are far from calm. They are restless, shifting realms, constantly shaped by gravity's pull, the invisible grip of magnetic fields, and the violent energy of nearby stars. Magnetic fields weave through them like unseen threads, guiding the movement of charged particles and resisting the force of gravity. These fields help prevent a cloud from collapsing all at once, allowing new stars to form gradually instead of in one great rush. Meanwhile, shockwaves from exploding stars, supernovae, can ripple across space, squeezing parts of these clouds and setting off new waves of starbirth. This chain reaction, called triggered star formation, means that one generation of stars can give rise to the next. The fierce winds and bright radiation from newly born stars can carve the surrounding gas into glowing arcs and towering pillars, gathering some regions together while blowing others apart. Over millions of years, this constant struggle between opposing forces, gravity pulling inward, magnetic fields pushing back, radiation driving outward, and turbulence stirring the gas, sculpts molecular clouds into incredible shapes. Some stretch into long, thread-like filaments, others rise like stone columns, and some hollow out into huge bubbles of glowing gas. These forms are not just beautiful to look at, they reveal the hidden processes that govern the birth of stars. When ultraviolet light from young, hot stars strikes the surrounding hydrogen gas, it makes the gas glow, forming what astronomers call emission nebulae. But in places where the gas and dust are too thick for light to pass through, we see dark nebulae, shadowy shapes that block the light behind them. Both kinds of nebulae tell parts of the same grand story, the Milky Way constantly renewing itself through creation and destruction. Molecular clouds lie at the heart of this process. They are the starting points of stars and planets and play a vital role in the life of the galaxy. When old stars die, some gently blowing away their outer layers, others exploding in violent supernova, they release gas and dust rich in heavy elements like carbon, oxygen, silicon and iron. This material mixes with the existing interstellar gas and eventually gathers again into new molecular clouds. Over time, these clouds collapse, forming new stars and planetary systems. When those stars die, the cycle repeats. This endless rhythm of birth, death and rebirth has been going on for billions of years, keeping the Milky Way alive and ever-changing. Above and below the solar system, molecular clouds quietly perform this cosmic duty. They are the nurseries of the universe, preparing the next generations of stars that will shine for millions or even billions of years. Our own story began in such a place about 4.5 billion years ago, when a cloud of gas and dust collapsed under gravity to form the young sun, surrounded by a swirling disk of material that would become the planets, moons and comets we know today. In that sense, molecular clouds are not distant curiosities. They are the birthplace of everything we see around us. Every atom in our bodies, every grain of sand on Earth, and every drop of water once passed through this ancient cycle of stellar life and death that begins in these mysterious clouds. These clouds are also natural laboratories for chemistry on a cosmic scale. Because they are cold and protected from harsh radiation, they provide the perfect environment for molecules to form and survive. Using telescopes that detect radio, infrared, and submillimeter waves, scientists have discovered more than 200 different molecules inside them. Some are simple, like water and carbon monoxide, while others are surprisingly complex. Organic compounds such as methanol, formaldehyde, ethanol, and even basic sugars. These molecules may one day become part of forming planets or comets, carrying the seeds of life to distant corners of the galaxy. Astronomers study these hidden worlds with powerful instruments on Earth and in space. Since visible light cannot pass through their thick dust, researchers rely on other types of radiation, radio and infrared waves that can pierce the darkness. Observatories such as the Atacama Large Millimeter Array in Chile and the Herschel Space Observatory have mapped the inner structures of these clouds in remarkable detail. They show that a single cloud can contain many layers, some cold and quiet, others hot and turbulent. This variety helps explain why star formation happens in clusters and bursts rather than evenly everywhere. The behaviour of these molecular clouds is deeply connected to the Milky Way's grand design. The spiral arms of our galaxy, which wind gracefully through space, are shaped partly by the presence of these clouds. As the Milky Way slowly turns, regions of higher density in the spiral arms squeeze gas and dust together, creating new clouds. These then form stars, whose light outlines the arms and keeps their spiral shape visible. Between the arms, where there is less gas and dust, star formation slows down. In this way, molecular clouds help sculpt the very face of our galaxy. As the solar system travels around the centre of the Milky Way, it also drifts gently above and below the galactic plane in a slow, wave-like motion that takes tens of millions of years to complete. During this journey, the solar system sometimes passes through dense regions filled with molecular clouds, and at other times moves through emptier stretches of interstellar space. Though these clouds usually lie far from us, they still influence the wider galactic environment. The amount of gas and dust around the Sun affects the movement of cosmic rays, the behaviour of interstellar radiation, and even the shape of the heliosphere, the vast bubble of charged particles blown outward by the solar wind. The way molecular clouds are arranged above and below the Milky Way's main disk gives astronomers a deeper understanding of the galaxy's true three-dimensional shape. The thickest and heaviest clouds tend to stay close to the galactic plane, the crowded, bright region where most new stars are born. Higher above and below this plane, the clouds become thinner, more scattered, and more fragile, slowly blending into the faint glow of the galactic halo that surrounds the Milky Way like a ghostly mist. This layering is not random. It shows how gravity, pressure, and turbulent motion balance one another across the galaxy, much like the way air forms different layers in a planet's atmosphere. By examining this vertical structure, scientists can learn how gas and dust move between the Milky Way's different regions and how the galaxy keeps its delicate stability over billions of years. Each molecular cloud is like a vital link in the endless chain of cosmic creation. Inside them lies both the remains of long-dead stars and the seeds of new ones yet to come. When a massive star lives out its brief but brilliant life, it eventually dies in a colossal explosion called a supernova. This explosion sends its heavy elements, such as carbon, oxygen, and iron, rushing out into space, enriching the surrounding gas clouds. The next generation of stars that forms from this enriched material carries within it the chemical gifts of the past. This ongoing process explains why younger stars, like our own Sun, contain more heavy elements than older stars. Over time, through countless cycles of birth, death, and renewal, this transformation has turned the Milky Way from a galaxy made mostly of hydrogen and helium into one filled with a rich variety of elements, the same ingredients that form planets, oceans, and even living creatures. Though molecular clouds may appear dark and lifeless, they are anything but still. They are restless realms of swirling motion, hidden energy, and constant change. Within them, gravity pulls gas together while internal pressure and magnetic fields push it apart, creating a delicate balance that decides when and where stars will form. Some clouds remain calm and quiet for tens of millions of years, drifting peacefully through space, while others are suddenly stirred into action by shock waves from nearby supernovae or by gravitational forces from passing stars. These differences give rise to the variety of stellar nurseries seen across the Milky Way, from the soft, faint clouds in the constellation of Taurus to the vast and chaotic star-forming regions of Orion and Carina, where new suns ignite in blinding brilliance. When scientists observe molecular clouds using radio telescopes, they do not see simple shapes, but elaborate webs filled with tangled filaments, dense knots, and hollow spaces. Computer models suggest that these patterns emerge naturally from the interplay between gravity, turbulence, and magnetic energy. Despite their wild appearance, there is an underlying order in how stars form within these clouds. Across the Milky Way, the number and size of stars that form follow predictable mathematical patterns. This remarkable regularity reveals that, even in the seeming chaos of space, the universe operates according to steady and precise laws that guide the birth of stars and the evolution of galaxies. Studying molecular clouds is not just about understanding the clouds themselves, it reaches into some of the deepest questions about existence. Through them, scientists explore how galaxies take shape, how planets emerge, and even how life may begin. By tracing the journey of matter from thin interstellar gas to dense molecular clouds, then to stars, planets, and eventually living organisms, astronomers can piece together the great story of cosmic evolution, a story that connects the tiniest molecule to the grandest galaxy. The molecular clouds that float above and below our solar system are not just silent, cold collections of gas. They are the hidden engines of creation. Within their dark depths, the most extraordinary process in nature unfolds, the birth of stars. They supply the raw material for everything we see shining in the night sky. They control the rhythm of the Milky Way's life cycle, carrying within them the chemical memory of countless generations of stars long gone. Through them, we learn that our galaxy is not a still and lifeless collection of stars, but a living, breathing system, one that constantly renews itself through cycles of destruction and creation, forever shaping the universe we call home. The Galactic Plane is the grand foundation and central sheet of our home galaxy, the Milky Way. It is far more than just a flat layer of stars. It is a vast, thin, and shining disk made up of uncountable stars, gigantic clouds of gas, and delicate grains of cosmic dust spread across unimaginable distances. This immense disk gives the Milky Way its graceful spiral form, with long, curving arms that swirl outward from the dense and glowing galactic center. It is within this great plane that the galaxy truly comes alive, for it is here that most of its light, motion, and creation take place. When astronomers look through their telescopes toward this great disk, they see almost everything that defines our galaxy: brilliant young stars burning fiercely, glowing nebulae where new stars are born, and vast clusters containing hundreds or even thousands of suns held together by gravity. The Galactic Plane is the Milky Way's beating heart, where energy flows, stars are created, and cosmic forces constantly shape new wonders. From our small world on Earth, when we look up into the night sky, we can see this same galactic plane as a soft, glowing ribbon of light stretching from horizon to horizon. To the unaided eye, it looks like a faint cloud, but it is actually made of billions of distant stars packed so closely together that their light blends into a continuous glow. This shining band gave our galaxy its name, the Milky Way. Every star within that glowing stripe belongs to the grand disk of our galaxy, and our own sun is one of those countless points of light. Our solar system lies deep within this immense and delicate plane. It travels in a wide, nearly circular path around the galactic center, completing one full journey in hundreds of millions of years. But this motion is not as simple as moving in a flat ring. Our solar system's path is full of graceful complexity. It is shaped by the pull of nearby stars, the presence of enormous molecular clouds of gas, and the mysterious gravity of dark matter that surrounds and threads through the galaxy. These subtle interactions slowly alter its movement, guiding it gently through space over immense spans of time. The galactic plane itself is astonishingly thin when compared to the full height of the Milky Way. Nearly all the stars, gas, and dust are gathered within this narrow band, while much less material lies far above or below it. Because of this, astronomers think of the galactic plane as a kind of cosmic equator, an invisible dividing line that defines what they mean by above and below the Milky Way. These directions have no true meaning beyond this great flat structure, but they help us describe our position within the galaxy. Yet this grand plane is not still or motionless. It is alive and full of change. As the solar system moves around the galaxy's heart, it passes through regions of different density and brightness, some rich with stars and glowing gas, others dark and nearly empty. Along the way, it encounters brilliant star clusters, drifting interstellar clouds, and even the faint gravitational tugs of wandering stars that slightly bend its path. These endless interactions help to shape how matter is arranged within the plane, and even influence when and where new stars are born. Above and below this busy plane, the galaxy grows quieter and more peaceful. The regions there are home mostly to older stars that have drifted out of the dense disk. The matter in these areas is thinly spread, and the galactic air, so to speak, is calm. This sharp contrast between the crowded, energetic plane and the quiet, airy regions above and below gives the Milky Way its layered, three-dimensional beauty. By studying the galactic plane, astronomers learn how the Milky Way is built and how it changes over time. It acts as the baseline for mapping the vertical structure of the galaxy. showing how stars, gas, dust, and even dark matter are arranged above and below this invisible sheet. Through these studies, scientists can uncover how gravity shapes the galaxy, how new stars are formed, and how all the parts of the Milky Way move and evolve together. Though it might seem that the solar system glides smoothly along the flat disk, its movement is far more intricate. In truth, it follows a slow, wave-like path, gently rising above and then sinking below the galactic plane, a rhythm known as vertical oscillation. This subtle up and down motion is caused by the pull of gravity from the thick layer of stars, gas, and dark matter that fills the disk. The result is a smooth and graceful journey that never truly stops. Each full cycle of this vertical motion takes an astonishing amount of time, around 60 to 70 million years to go from below the plane, rise above it, and then return again. Over that long period, the solar system reaches a gentle peak above the galactic plane before slowly falling back through the crowded central layer and descending to the opposite side. This motion continues endlessly, repeating like the heartbeat of the galaxy itself. The movement is calm and continuous, not wild or chaotic. It resembles a soft wave that the solar system rides as it circles the galactic center. The galactic plane serves as the middle balance point, the line our solar system crosses every few tens of millions of years as it rises and falls in this slow cosmic dance. In this way, our system does not simply orbit in a flat circle, it moves in a graceful rhythm, as though breathing in harmony with the Milky Way. This long rhythmic motion can be compared to vast galactic seasons. Just as Earth experiences spring, summer, autumn, and winter as it travels around the Sun, the solar system passes through great cycles as it moves through different layers of the Milky Way. When it drifts through the denser parts of the galactic plane, it passes regions thick with gas and dust, where the surrounding cosmic environment becomes slightly more active. During these times, the solar system might encounter stronger flows of cosmic rays or feel faint gravitational effects that can disturb the distant Oort cloud, sometimes sending icy comets inward toward the inner planets. When the solar system moves farther from the plane into the upper or lower regions of the galaxy, it enters areas that are much emptier and quieter. Here, there is little gas or dust, and the cosmic environment becomes calm and clear. The space around us changes, becoming less crowded and more peaceful. This means that the solar system's surroundings, the neighborhood of stars and interstellar matter, are never the same for long. Over millions of years, they shift as we rise and fall through the galaxy's great layers. The idea of vertical oscillation helps astronomers better understand what it truly means when they talk about above and below the Milky Way. These directions are not random, they are defined by the galactic plane itself, the great flat disk that forms the body of our galaxy. When astronomers say above, they mean one side of this disk, and when they say below, they mean the opposite side. The solar system moves gently up and down through these directions as it orbits the galactic center, and this movement gives scientists valuable clues about how the stars, the clouds of gas, and even the mysterious dark matter are arranged all around us. By studying this motion, astronomers can build a three-dimensional picture of the Milky Way, one that reveals not just its beautiful spiral shape, but also its vertical depth and hidden structure. Over the course of tens of millions of years, this slow bobbing motion has a subtle but powerful effect. As the solar system passes through the galactic plane, it enters regions that are rich in cosmic material, dense with dust, gas, and energy. When it rises or falls away from the plane, it moves through quieter regions, where space grows thinner and emptier. These vast changes happen so gradually that no person could ever sense them in a single lifetime, yet they shape how our part of the galaxy evolves over immense stretches of time. This endless motion reminds us that nothing in the universe is ever still. Every star, every drifting cloud of gas, every planet and moon is constantly moving, all bound together by the invisible pull of gravity. Even the Milky Way itself, so vast and ancient, is not fixed in place. It twists, it breathes, it ripples with the movement of countless stars and clouds. The solar system's gentle rise and fall through the galactic plane is just one small part of this grand and graceful motion, a rhythm in the great cosmic dance that fills the universe with life and energy. The galactic plane is far more than a simple flat sheet of stars. It is the heart and foundation of the Milky Way, the great stage where stars are born from clouds of gas and dust, where others burn brightly before fading into darkness, and where the cycle of creation and destruction never ends. It is within this magnificent arena that gravity weaves the fabric of our galaxy, shaping everything that shines in the night sky. Our own sun and planet are not spectators but participants, carried along in this vast celestial current alongside billions of other stars. As the solar system continues its slow drift above and below the immense galactic disk, it takes part in the Milky Way's never-ending story. Over tens of millions of years, it moves through ever-changing regions, sometimes dense and filled with raw material for new stars, and sometimes thin and peaceful, where space seems almost empty. Each motion, whether around the galactic center or across the galactic plane, reveals that the universe is a living ocean of motion and energy, flowing on scales far beyond human imagination. High above the main plane of the Milky Way, space begins to change gradually. The tightly packed region filled with stars, gas, and dust slowly fades into areas where these materials become more scattered and less concentrated. Yet even in these upper regions, the presence of the thin disk, the Milky Way's main and most active structure, remains strong. This disk extends several hundred light-years above the central plane and forms the heart of our galaxy's creative activity. Within this wide, flattened layer, most of the Milky Way's stars, gas, and planetary systems are born. Here lie the bright, energetic, and youthful stars that give our galaxy its lively and ever-changing character. Many of them are quite similar to our own Sun, and by studying these stars, astronomers gain valuable insight into how solar systems form, grow, and spread throughout the galaxy. From a cosmic point of view, the stars that make up the thin disk are considered relatively young. Most of them are younger than 10 billion years old, a time span that represents only a portion of the Milky Way's long and complex history. These stars come in many different types, showing a wide range of colours, temperatures, and sizes. Among them are huge, blazing blue giants that burn with incredible brightness and heat, as well as smaller and steadier yellow dwarfs like our Sun, which shine gently and consistently for billions of years. Because new stars continue to form here, the thin disk is one of the most active and vibrant parts of the galaxy, constantly renewing itself through cycles of birth and transformation. Within this region, countless open clusters can be found, groups of stars that were born together from the same enormous cloud of molecular gas. These clusters are held together loosely by gravity and gradually drift apart over time, though they still share similar ages and chemical compositions. Astronomers view them as natural laboratories that reveal the life stories of stars. By observing these clusters, scientists can trace how stars develop from their earlier stages to maturity, how heavy elements are created deep within stellar cores, and how these elements are later released to enrich the galaxy. Open clusters also offer important clues about the birth of planetary systems, since many of their stars are surrounded by rotating disks of gas and dust that may eventually form new worlds. Although the thin disk dominates the area above the galactic plane, it is surprisingly flat and delicate compared to the Milky Way's vast spherical halo. It stretches a few hundred light-years above and below the central plane, appearing almost like a shining cosmic sheet when viewed from afar. Within this flattened structure lie billions of stars spread unevenly across space. The number of stars decreases gradually with height above the galactic plane, forming a gentle thinning that marks the disk's upper boundary. Most stars are concentrated near the middle region, but the areas above and below still play a vital role in supporting the Milky Way's overall structure and energy. The thin disk above our solar system is especially important because it contains stars rich in heavier elements, substances that were formed inside earlier generations of stars and scattered into space when those stars died. In astronomy, all elements heavier than hydrogen and helium are called metals, even though they include familiar elements like oxygen, carbon, silicon, and iron. These metals are essential for the creation of solid planets, atmospheres, and possibly life itself. The stars in the thin disk tend to have higher metallicity than those found in older regions like the thick disk and the halo, which shows that this area has been enriched by countless cycles of stellar birth, death, and renewal over billions of years. Along with its countless stars, the thin disk contains enormous amounts of interstellar gas and dust, which together form what astronomers call the interstellar medium. Far from being an empty void, this medium is filled with vast clouds of hydrogen and helium, along with traces of carbon, nitrogen, oxygen, and many other elements. Under the pull of gravity, parts of these clouds can collapse, leading to the birth of new stars. Because the density of gas in the thin disk remains high enough to support these collapses, it serves as the galaxy's main nursery for star formation. Within these regions, gravity, turbulence, and radiation interact to form beautiful and complex shapes that often glow brightly in infrared and radio light, silent but powerful signs of creation taking place. By studying the thin disk that lies above our solar system, astronomers can learn much about the Milky Way's overall behaviour, how it rotates, how its stars move, and how its grand spiral arms slowly evolve over time. Most of the stars in this region travel in smooth, nearly circular orbits around the galactic centre, following a similar path to that of our Sun. This organised motion helps the thin disk maintain its flat, balanced shape. However, over millions of years, tiny gravitational influences cause stars to drift inward or outward, changing their positions and mixing the disk's contents. These small, slow shifts ensure that the thin disk never remains completely static, but instead continues to change and grow with time. Our solar system's place within this active region means that it is constantly surrounded by cosmic events. One of the most dramatic of these events is the supernova, the brilliant explosion that marks the end of a massive star's life. Such explosions happen regularly within the thin disk, each releasing unimaginable amounts of energy, fast-moving particles, and newly formed heavy elements into space. Supernovae play a crucial role in the Milky Way's ecosystem. They spread metals that enrich the interstellar medium, send shock waves that trigger the birth of new stars, and sometimes even disturb the orbits of nearby stars through their intense gravitational effects. In this way, the thin disk remains a region of both creation and destruction, a place where the cycle of life and death among the stars keeps the Milky Way alive, glowing and ever-changing. Many of the stars within the thin disk also have planetary systems outside our solar system. In recent years, astronomers have found thousands of such systems across the galaxy, and many of them belong to the thin disk. Because these stars often share similar chemical features with our Sun, they are good candidates for having planets like Earth. This makes the area above the solar system especially interesting for the study of life beyond our planet. The large amount of metals and the presence of steady, long-living stars increase the chances of rocky planets with air and liquid water, which are key conditions for life as we know it. In this way, the thin disk above us may contain many worlds like our own, circling distant suns spread across the Milky Way. In shape, the thin disk is not even or uniform. It has detailed patterns that show its active past. Among these are the spiral arms, huge curved bands of stars and gas that stretch outward from the centre of the galaxy. These arms are not solid objects but areas where waves of density squeeze gas and cause bursts of starbirth. Between the arms are calmer zones where older stars are more common. Inside the disk are also star streams, groups of stars that travel together through space, often the leftovers of smaller galaxies that joined with the Milky Way billions of years ago. The thin disk also shows the marks of these old collisions, with clusters of stars that still hold the memory of long-lost galactic neighbours. By studying the stars above the Galactic Plane, astronomers can trace how the Milky Way rotates, showing how fast different parts of the galaxy spin. This information helps scientists measure how mass is spread out, including both the visible matter like stars and gas, and the unseen dark matter that pulls with gravity but gives off no light. Watching how stars move up and down above the plane also gives hints about the galaxy's overall gravity and how our solar system moves up and down through the disk over millions of years. Together, these studies create a detailed three-dimensional view of the Milky Way's shape and history. As one moves farther above the galactic plane, the thin disk slowly changes into the thick disk, a region filled with older, more widely spaced stars. The edge between the two is not sharp but gradual, where young metal-rich stars give way to old, metal-poor ones. Yet directly above our solar system, the thin disk still dominates. Here, fairly young stars and active star-forming areas still shine, making this layer the most lively and important part of the Milky Way's vertical structure. The thin disk shows the current stage of the galaxy's life, a place of constant change where gravity, light and chemistry work together to form new worlds. Even though it seems huge, the thin disk is actually quite narrow compared to the total height of the galaxy. This thinness shows the fine balance that defines our solar system's position in the Milky Way. We live in a layered area where gravity holds everything together, yet motion and change constantly reshape our surroundings. Above us, stars move in large circles, gas clouds drift and collapse, and light from faraway clusters travels for centuries before it reaches our eyes. It is a neighbourhood both fragile and beautiful, held together by the unseen forces of galactic motion. Studying the thin disk has real uses beyond theory. When astronomers map the Milky Way with visible light, infrared rays or other kinds of radiation, the thin disk stands out as one of the brightest areas, second only to the galactic centre. Infrared studies are especially useful because they can pass through thick dust clouds that block visible light, showing hidden stars and the complex web of gas above the plane. By studying these stars, scientists can measure how fast new stars are being born, estimate the ages of star groups, and track how matter moves through the galaxy. This helps build a full model of how the Milky Way changes over time. In the thin disk, every part of the cosmic cycle can be seen. Stars are born from gas clouds, live for millions or billions of years, and then return their material to space through stellar winds or explosions. That recycled material becomes the starting point for new stars and planets. The process repeats endlessly, each round adding more detail and richness to the galaxy. The thin disk above the solar system represents this ongoing renewal, a vast, glowing workshop of creation that has lasted for countless ages. Astronomers have learned that the stars in the thin disk differ not only in age, but also in movement and chemistry. Some stars move in almost perfect circles, while others show small tilts or vertical movements. These differences reveal past events that disturbed the galactic disk, such as smaller galaxies passing by, or waves of star formation spreading through the spiral arms. The chemical makeup of stars in the thin disk also tells the story of how the Milky Way grew. Younger stars have more heavy elements, showing that each new generation builds on the remains of the one before. By comparing the metal content of stars at different heights above the plane, scientists can trace how the galaxy became richer in elements over billions of years. The area above the galactic plane also gives a look into how the Milky Way's gravity behaves. Stars and gas clouds do not stay still. They move under the pull of the galaxy's total mass. Our solar system, for example, slowly moves up and down through the galactic midplane in a cycle lasting tens of millions of years. During this time, it passes through areas of different density, feeling small changes in gravity. These motions may even affect the flow of comets in the outer solar system by disturbing the Oort cloud, showing how deeply our local region is connected to the galaxy's overall structure. Above the plane, astronomers also find faint traces of high-energy light, the remains of supernovae, and bubbles in space carved out by massive stars. These events make the thin disk look active and ever-changing. They heat nearby gas, send shockwaves through space, and sometimes create superbubbles, huge empty areas filled with hot plasma that can stretch for hundreds of light years. These shapes are the marks left behind by past generations of giant stars whose deaths helped form the disk we see today. From an observational point of view, the thin disk is one of the richest sources of data in the sky. When telescopes scan the heavens, the crowded starlight of the thin disk forms the bright band we call the Milky Way, visible to the naked eye on a clear night. Through telescopes that detect radio waves or infrared light, this band reveals hidden structures, webs of gas, dark paths of dust, and glowing clouds where stars are being born. Each observation adds another piece to the puzzle of how the galaxy stays balanced between order and chaos, collapse and growth, death and creation. The study of the thin disk also helps us understand the Milky Way's future. Over billions of years, the ongoing activity within this layer will keep shaping the galaxy. Stars will form, live, and die. Spiral arms will shift and change, and gravity will slowly rearrange the stars. Knowing how the thin disk works is key to predicting how the Milky Way will look far in the future and how our solar system fits into that big picture. In the end, the thin disk above the galactic plane is much more than a region of stars. It is a living system, always changing and renewing itself. It holds the materials for planets, the ingredients for life, and the record of countless cosmic events. Every star above us carries the story of generations of explosions, mergers, and births that came before. Every atom of iron or carbon in our bodies was once made inside a star like those shining in the thin disk. So studying the area above the galactic plane is not just astronomy. It is a way to understand our own place in the universe. The thin disk represents the Milky Way's living heart, where gravity, light and chemistry work together to create the wide variety of stars and worlds in our galaxy. From its rich clusters and spiral arms to its calm, empty spaces, it forms a continuous system that links the smallest grains of dust to the largest stars. Above our solar system, this region keeps shining with activity, continuing the timeless process of creation that has shaped the Milky Way since its beginning. Through careful study of its stars, gas and movement, people gain not only knowledge of the galaxy's structure, but also a deeper sense of the cosmic home that made us. The thin disk above the galactic plane stands as a bright reminder of the Milky Way's living energy. It connects the familiar world of the solar system with the vast reaches of space, linking our local area to the great cosmic story unfolding across billions of light years. Within its layers lie the clues to the Milky Way's past, the forces shaping its present, and the seeds of its future. A never-ending dance of matter and energy that continues above and around us. Below the galactic plane of the Milky Way, the shape of our galaxy changes slowly but clearly, moving from the young, bright and active regions of the thin disk to the older, quieter, and more spread out area known as the thick disk. This lower layer of the galaxy is not as crowded or as active as the thin disk above, but it holds a deep and ancient history that goes back almost to the time when the Milky Way first began to form. While the thin disk, the region that contains our solar system, is filled with fairly young stars, glowing clouds, and zones where new stars are still being born from gas and dust, the thick disk represents a much older part of the galaxy's story. Here, the stars are ancient, their light dim and steady rather than bright and blue. Most of these stars are between about 8 and 12 billion years old, meaning they formed during the early stages of the Milky Way, long before the Sun or Earth existed. The thick disk stretches much higher and lower than the thin disk, reaching thousands of light years above and below the galactic plane. Its stars are spread out more thinly, creating a region with fewer visible stars. Instead of the thick, bright lanes of stars that fill the thin disk, this lower area looks faint and hazy, like a ghostly part of the galaxy's main body. But even though it seems dim and quiet, the thick disk holds some of the most important clues about the Milky Way's early life. The stars within it are like living fossils, keeping in their makeup and motion the record of how the galaxy first came together from smaller bits of matter and gas. Their outer layers hold signs of the materials that were around when they were born, showing what processes took place during the Milky Way's early years. Unlike the thin disk, where most stars move in nearly circular paths around the centre of the galaxy, the stars in the thick disk follow more uneven orbits. Their paths are more oval-shaped, and they tilt at different angles compared to the plane of the galaxy. This gives the thick disk its puffed-up look, as stars wander higher or lower above and below the main galactic plane. Their wider range of speeds and directions suggests that they were either formed during a more chaotic time or were shaken up later by strong gravitational effects. Many astronomers believe that ancient collisions with smaller galaxies, long absorbed by the Milky Way, helped shape this layer. When these small systems crashed into our galaxy billions of years ago, their gravity likely disturbed existing stars and mixed them together, forming the thicker, more spread out layer we see today. The stars in the thick disk are usually smaller, dimmer, and redder than the ones in the thin disk. Many of them are red dwarfs, small cool stars that burn their fuel slowly and can live for hundreds of billions of years. Others are white dwarfs, the remains of stars that once shone brightly but have now used up their hydrogen and collapsed into dense, Earth-sized cores. Some are subgiants or red giants, older stars that are in between stages of their life, glowing faintly as they approach the end of their existence. Compared to the bright blue-white stars of the thin disk, these older stars give off softer, redder light, which makes the thick disk look dimmer through telescopes. One major difference between the two disks is their metallicity, that is, how many heavy elements they contain. Stars in the thick disk usually have fewer heavy elements like iron, carbon, or oxygen. This is because they formed a very long time ago, before many generations of exploding stars, supernovae, had filled space with these heavier elements. In the early universe, most stars formed from pure hydrogen and helium left over from the Big Bang. As stars lived and died, they made heavier elements and spread them into space. Newer stars, like our Sun, formed from this enriched gas, and therefore contain more heavy elements. But the stars in the thick disk have very few of these elements, making them ancient relics from a time when the Milky Way was still young and forming from the first simple materials. By studying what these old stars are made of and how they move, astronomers can piece together the Milky Way's long history. Each thick disk star acts like a time capsule, holding clues about the conditions when it was born. The mix of elements inside them helps scientists figure out what kinds of stars exploded nearby back then, and how those explosions shaped their surroundings. Their movements also reveal how the galaxy's gravity works, how massive it is, and how matter, both visible and invisible, is spread across it. Because the orbits of thick disk stars reach high above and below the galactic plane, they are affected by the galaxy's overall gravitational shape, including the hidden dark matter halo that surrounds it. Tracking their paths helps astronomers estimate how much dark matter exists and how it is arranged throughout the Milky Way. The thick disk is not just a leftover from the past. It still interacts with other parts of the galaxy. Gravity links it to both the thin disk and the outer halo. Sometimes, stars from the thick disk move through the galactic plane and mix with younger stars in the thin disk. Likewise, some thin disk stars are pushed into higher orbits and temporarily join the thick disk. This constant exchange shows that the Milky Way is not still or quiet. It is an active, changing system where all its layers affect each other. These movements help the galaxy stay balanced while slowly evolving over billions of years. Since the thick disk stars are older, many have already used most of their hydrogen fuel. A large number have turned into red giants, cooler, swollen stars that shine more brightly as they fuse heavier elements inside. Others have become subgiants or white dwarfs. Even though they are dimmer than the younger, hotter stars above, these ancient stars are very important to astronomers. Because they are so old, they help trace the Milky Way's earliest history. They may not add much to the galaxy's total brightness, but they outnumber the younger stars of the thin disk by far, especially across the great height of the thick disk. This creates a layered look when we observe the Milky Way. The upper parts of the galaxy glow brightly with young stars forming in spiral arms, while the areas below the plane are quieter, filled with older stars that stretch deep into space. Together, these layers form a vertical pattern of age, brightness, and chemical richness, a living cross-section of the galaxy's evolution. The thick disk stands as proof of how the Milky Way grew from a simple, gas-filled system into the grand spiral we see today. Farther down, the thick disk gradually blends into the halo, a large round region surrounding the whole galaxy. Some thick disk stars have wide orbits that connect these two zones. In this border region, astronomers have found traces of old galactic collisions, streams of stars moving together through space that once belonged to smaller galaxies. These were absorbed by the Milky Way long ago. Their motions and chemical makeup are slightly different from stars born in our galaxy, showing that they came from outside. Each ancient merger left behind faint marks in the thick disk, like scars from cosmic impacts. In this way, the thick disk acts as both a record and a witness to the Milky Way's stormy past. Its stars hold signs of the powerful events that shaped the galaxy we live in today. Some were flung into their current positions during early galactic mergers, while others were born right inside the Milky Way from gas heated and mixed by those same collisions. The thick disk is therefore not a simple, uniform layer. It is a complex mix of stars with different origins, all telling parts of the same story of how our galaxy grew. Besides individual stars, the thick disk also contains a few loose star groups called open clusters, collections of stars that form together but are slowly drifting apart, as well as remains of ancient globular clusters whose outer layers were pulled away by the galaxy's gravity. Some of these remains now appear as long, stretched-out streams of stars across the sky. These features show how the thick disk links the thin disk above with the halo beyond, acting as a bridge between regions of active star formation near the plane and the older, more spread-out halo farther out. The thick disk is dimmer and less crowded than the thin disk, but it plays a vital role in shaping the Milky Way's overall form. It shows that the galaxy is not just one flat sheet of stars, but a layered system made of different kinds of stars separated by age, movement, and chemical makeup. Without the thick disk, our view of the Milky Way would be incomplete. Its stars help astronomers understand what below the plane really means, and how the galaxy's structure changes as we move away from the center and the midplane where our sun lies. From a wider point of view, the thick disk reminds us that our solar system is only one small part of a huge, many-layered galaxy. Above us lies the thin disk, glowing with bright young stars, clusters and nebulae. Below us is the thick disk, filled with ancient stars whose faint light carries the memory of the past. Beyond that stretches the dark halo, made mostly of unseen matter, scattered star clusters, and faint streams marking the galaxy's outer limits. These layers are all connected, held together by gravity and by the shared history of how the Milky Way formed. The connection between these layers shows just how complex our galaxy truly is. The thick disk, once thought to be a simple part of the Milky Way, is now known to be a key to its history. Its stars show that the galaxy didn't form all at once but grew slowly through mergers, collapses, and repeated cycles of star birth and death. Each generation of stars added more heavy elements to space, changing the material from which new stars would form. Over billions of years, this process created the layered structure we see today. Young, metal-rich stars in the thin disk, older, metal-poor stars in the thick disk, and ancient relics in the halo. The thick disk is also very useful for observation. Because its stars are faint and spread out, astronomers study them using infrared and spectroscopic tools that can see through dust and reveal their makeup. By measuring their metallicity, temperature and motion, scientists can estimate their ages and learn where they came from. Three-dimensional surveys of the thick disk have shown how star density decreases with height and how their chemical makeup changes from top to bottom. By studying the stars below our solar system, researchers can tell which ones may have come from other galaxies long ago. This work shows that the Milky Way didn't grow smoothly. It was built through many collisions and mergers over time. Some of the stars in the thick disk were once part of smaller galaxies that were absorbed by ours. Their chemical patterns are clues to those ancient events. All this information helps build a clearer picture of the Milky Way's mass and the spread of both visible and dark matter. Because thick disk stars travel farther from the galactic plane, they're especially useful in studying dark matter. By measuring how fast they move, astronomers can estimate the shape and thickness of the dark matter halo around the galaxy. This helps improve models of how galaxies form and change throughout the universe. When seen together, the thin and thick disks create a beautiful picture of cosmic layering. The thin disk represents youth and activity, while the thick disk stands for age and memory. The two are tied not just by gravity but also by their shared past. The thick disk may have given rise to the first stars that later helped form the thin disk. In this way, the older layer continues to influence the younger one even after billions of years. The thick disk is much more than just a dim part beneath the galactic plane. It is a vital chapter in the Milky Way's story. Its stars act as historians, keeping the record of how the galaxy began and changed. Their faint light carries memories of ancient collisions and the long process that shaped the spiral galaxy we see today. Studying them is like looking back through time, seeing the early days of our galactic home. Every red dwarf, every white dwarf, every slow-moving star below the plane is a survivor from a distant era. Together, they form a living archive written in light and motion. By studying them, astronomers can better understand how galaxies form, grow, and change. The thick disk is one of the Milky Way's oldest storytellers, its quiet stars whispering tales of creation, growth, and the endless pull of gravity that continues to shape the universe today. The region below the galactic plane is not just an empty extension of space. It is a deep, ancient layer full of meaning. It connects the young brightness of the thin disk above with the dark mystery of the halo beyond, joining the Milky Way's past, present, and future. Understanding this layer is essential to understanding our galaxy itself, for it shows the Milky Way's vertical structure and reminds us that even in the dim depths below the plane, the universe is still alive with the echoes of creation. Far above and below the flat disk of the Milky Way lies a vast and mysterious region known as the Galactic Halo. Within this enormous space drift strange and restless formations called high-velocity clouds, often shortened to HVCs. These gigantic clouds are mostly made of neutral hydrogen gas, the simplest and most common element in the universe, the same material that once filled the early cosmos. What makes these clouds so fascinating is the incredible speed at which they travel. Some rush through space at hundreds of kilometers each second, far faster than the usual, orderly rotation of the Milky Way. While most interstellar clouds move smoothly in the same direction as the rest of the galactic disk, high-velocity clouds behave as if they are following their own mysterious paths. They may plunge toward the galactic plane or soar away from it, defying the predictable rhythm of the galaxy's gravitational dance. Their unpredictable movement makes them some of the strangest and most puzzling features surrounding our home galaxy. Even after many decades of observation and research, astronomers are still uncertain about where these fast-moving clouds truly come from. Various ideas have been proposed, yet none can fully explain all of their strange behaviours. What is clear, however, is that these clouds play a crucial role in the Milky Way's continuing life story. Many scientists believe that they act as a kind of cosmic supply line, bringing in fresh gas that fuels the formation of new stars. In this way, they are part of the great cycle of creation and renewal that keeps the galaxy alive, helping to recycle the basic materials that form stars, planets, and perhaps even the ingredients of life itself. High-velocity clouds come in many different shapes and sizes. Some are small and compact, only a few hundred light-years wide, while others are so vast that they stretch for tens of thousands of light-years across the heavens. One of the best-known examples is the Smith Cloud, a huge river of hydrogen gas more than 11,000 light-years long. This colossal structure is currently speeding toward the Milky Way's disk at about 73 kilometers per second. Scientists are watching it closely because, in roughly 30 million years, the Smith Cloud is expected to collide with the Galactic Plane. When that happens, it may release a tremendous wave of hydrogen gas that could spark a new era of star formation, lighting up the galaxy with fresh stellar nurseries. Whenever a high-velocity cloud approaches the galactic disk, it can pour immense quantities of hydrogen gas into the interstellar medium, the space between stars where new ones are born. This process is vital because over billions of years, the Milky Way has gradually used up much of its original hydrogen through star formation. Each time a star forms, it consumes this gas and transforms it into heavier elements through nuclear fusion. Without new supplies of hydrogen, the galaxy's ability to create stars would eventually fade away. High-velocity clouds act as enormous refueling systems, continuously delivering this essential raw material and ensuring that the Milky Way never runs out of the fuel needed to give birth to new generations of stars. Although hydrogen makes up most of the material in these clouds, they also contain helium and small traces of heavier elements such as oxygen, carbon, and nitrogen. The amount of these heavier elements, known as metallicity, differs from one cloud to another. Some high-velocity clouds are poor in metals, suggesting they may have formed from untouched ancient gas that still drifts in intergalactic space, gas left over from the early universe before stars ever existed. Others are rich in metals, showing signs that they were once part of the Milky Way itself. These could be clouds of gas expelled from the galactic disk by powerful events such as supernova explosions or fierce stellar winds, now returning after long journeys through the halo. This wide variety in composition gives astronomers valuable clues about the history of each cloud and the grand processes shaping the Milky Way. By studying their chemical makeup and the way they move, scientists can trace how matter flows into and out of the galaxy. In doing so, they gain insight into how the Milky Way grows, how it keeps forming stars, and how it exchanges material with the wider universe beyond its borders. High-velocity clouds are not limited to a single side of the galaxy. They exist both above and below the galactic disk, scattered throughout the immense halo that surrounds the Milky Way. The galactic halo itself is an enormous, roughly spherical region, extending for hundreds of thousands of light-years in every direction. Inside this vast space are old stars, dense globular clusters, hot ionized gas, and even the mysterious pull of dark matter. As high-velocity clouds travel through the halo, their movement is guided not only by the gravity of visible stars and gas, but also by the invisible influence of the dark matter that envelops the galaxy like a hidden web. Some of the incredible speeds seen in these clouds may have been caused by ancient collisions with smaller galaxies. Over its long history, the Milky Way has swallowed many dwarf galaxies in a slow process called galactic accretion. The remnants of these collisions still wander through the halo as streams of stars and gas. High-velocity clouds may be the leftover gas torn away during these cosmic encounters. In some cases, they could even be pieces of small galaxies ripped apart by the Milky Way's strong tidal forces, flung across space at breathtaking speeds. As these clouds drift through the halo, they often interact with the thin, hot gas that fills this enormous region. These encounters can heat and compress the clouds, causing them to glow in different kinds of light. Astronomers can detect this radiation using various telescopes. The neutral hydrogen within these clouds, for instance, gives off a distinctive signal at a wavelength of 21 centimeters, an invisible radio wave that allows scientists to map their positions and movements. Observations in ultraviolet and X-ray light reveal even more details about the outer layers of these clouds, where cooler hydrogen mixes with the surrounding hot gas. By studying these faint glows, astronomers can uncover the temperatures, densities, and chemical properties of the high-velocity clouds, bringing them closer to understanding how these mysterious wanderers shape and sustain the Milky Way. One of the most fascinating things about high-velocity clouds is how deeply they are tied to the never-ending life cycle of our galaxy. The Milky Way, just like other giant galaxies scattered throughout the universe, is not a closed system. It constantly exchanges matter with the vast space around it. Streams of gas flow inward from the surrounding halo, bringing fresh material into the galactic disk, while powerful explosions such as supernova and strong stellar winds push gas outward again into the halo. This continuous exchange keeps the Milky Way alive and evolving. High-velocity clouds play a key role in this process. They carry new, low-metallicity gas that contains fewer heavy elements, into the galaxy, helping to keep star formation going for billions of years. Without these inflowing clouds, the Milky Way would eventually run out of hydrogen, the main fuel for stars, and its once bright regions of starbirth would slowly fade away. Some of these fast-moving clouds may even contain ancient, untouched material, gas that has remained nearly the same since the dawn of the universe. If that is true, these clouds are like time capsules, holding the original ingredients from which galaxies were born. Studying them gives astronomers a glimpse into what the universe was like not long after the Big Bang, helping to reveal how the first stars and galaxies began to form in those early cosmic ages. But the importance of these clouds is not only in the kind of gas they bring. When high-velocity clouds crash into the denser gas of the Milky Way's disk, the collisions can unleash dramatic effects. The impact creates shock waves that ripple through the surrounding medium, squeezing it and sometimes setting off the birth of new stars. In regions that were once quiet and still, these collisions can ignite sudden bursts of star formation, lighting up the sky with clusters of newborn suns. Because of this, high-velocity clouds act as both spark and regulator. They control when and where new stars appear, linking the calm outer halo with the energetic heart of the galactic disk. Astronomers detect and study these clouds mainly by observing the special radio signals given off by neutral hydrogen atoms. This signal, known as the 21 centimeter line, comes from a small quantum change within the hydrogen atom and allows scientists to trace cold, invisible gas throughout space. By carefully measuring this radiation, astronomers can map the cloud's speeds, positions, and shapes, even when they lie far beyond the reach of ordinary telescopes. Radio observations have revealed that some high-velocity clouds are small, isolated blobs, while others stretch across the sky as long, winding streams or filaments. Many of these enormous filaments appear to link the Milky Way's halo with its neighbouring satellite galaxies, such as the Large and Small Magellanic Clouds. One of the most famous examples is the Magellanic Stream, a vast ribbon of gas pulled away from those smaller galaxies by the Milky Way's gravity. High-velocity clouds inside this stream show that gas can move freely between galaxies, feeding the Milky Way with material that once belonged to its companions. This gradual transfer of matter, sometimes described as galactic cannibalism, is actually a normal part of how galaxies grow. Over billions of years, larger galaxies absorb smaller ones, adding their stars and gas to their own structure. In addition to these great streams, many smaller high-velocity clouds float throughout the halo like drifting islands of gas. Some may be the last remains of ancient shattered galaxies, while others might have condensed from the hot gas surrounding the Milky Way. Whatever their origins, they help scientists understand how matter circulates and transforms in this vast environment. The fact that such clouds exist above and below the solar system shows that the space around us is far from empty. It is alive with motion, filled with swirling gas and hidden energy that continuously shape the galaxy's structure. The movement of these clouds also gives scientists indirect clues about one of the biggest mysteries in astronomy: dark matter. Although dark matter itself gives off no light and cannot be seen, its gravity affects everything around it. By observing how high-velocity clouds move and accelerate, astronomers can estimate the shape and strength of the invisible dark matter halo that surrounds the Milky Way. These measurements make the clouds powerful tools for studying this unseen component of the universe, helping us understand how galaxies hold themselves together. In many ways, high-velocity clouds reveal that galaxies behave like living ecosystems. Just as life on Earth depends on the recycling of air, water, and nutrients, galaxies survive by constantly reusing their gas. Material flows inward from the halo to the disk, forming new stars, and then, after those stars die in supernova explosions, enriched gas is blown outward again into the halo. High-velocity clouds are one of the main channels in this cosmic recycling system. Through their constant motion, they keep the Milky Way active and capable of creating new generations of stars over unimaginable stretches of time. Above and below the familiar plane of the Milky Way, these clouds show that the galactic halo is anything but calm. It is a realm of turbulence and motion, where streams of gas and stars move in many directions, crossing paths like invisible rivers in the dark. The halo is filled with remnants of long-destroyed galaxies, drifting silently through space, and clouds of hydrogen speeding through the darkness with tremendous energy. High-velocity clouds are the visible signs of this restless motion, proof that even the seemingly quiet regions of space are full of activity and change. Modern technology has allowed astronomers to study these clouds in incredible detail. Giant instruments such as the Green Bank Telescope and the Very Large Array have mapped their locations across vast parts of the sky, identifying hundreds of individual structures. Each cloud is unique, with its own speed, shape, and chemical composition, and together they form a grand picture of how the Milky Way interacts with its surroundings. Observations show that some clouds slow down as they approach the galactic disk, possibly due to collisions with the hot gas in the halo. Others seem to be breaking apart, their material gradually mixing into the wider interstellar medium. In the end, most high-velocity clouds meet the same fate. They're absorbed into the Milky Way itself. As they fall toward the disk, they merge with the galaxy's gas, becoming part of the material that fuels new stars. Over time, their original forms disappear, but their contents live on as part of the Milky Way's ongoing cycle of birth and renewal. The clouds may be temporary, but their influence on the galaxy's evolution is lasting and immense, and the story does not end with our galaxy alone. Astronomers have detected similar high-velocity gas structures around many other galaxies throughout the cosmos. This shows that the processes happening here, gas exchange, star formation, and the shaping power of dark matter, are part of a grand universal pattern. By comparing the Milky Way's high-velocity clouds with those in distant galaxies, scientists can piece together how galaxies across the universe grow, change, and sustain themselves over billions upon billions of years. Though invisible to our eyes, high-velocity clouds are among the most important and dynamic parts of the Milky Way. They reveal that our galaxy is not an isolated island of stars but a living part of a vast cosmic web. Streams of gas stretch far beyond its visible boundaries, linking it to neighbouring galaxies and to the thin mist of intergalactic space itself. Through these invisible bridges, matter constantly flows in and out, shaping the Milky Way's destiny while preserving the ancient traces of its beginning. High above and far below the great disk of the Milky Way, the space that surrounds our solar system is anything but empty or silent. It is a restless and energetic region filled not only with stars and drifting clouds of gas, but also with many small neighbouring galaxies known as dwarf galaxies. Though these tiny companions may seem unimportant beside the enormous Milky Way, they play a powerful and ongoing role in shaping the structure and life of our galaxy. They are not just quiet clusters of stars floating in the darkness. They are active reservoirs of gas and chemical material that feed the Milky Way, and serve as living laboratories that help scientists uncover the ancient story of how galaxies form and change across the ages. These dwarf galaxies move above and below the galactic disk, carrying with them long trails of gas that can be pulled away and absorbed into the Milky Way's halo and disk. When one of these small galaxies drifts close to the main body of the Milky Way, the pull of gravity can strip its gas away, mixing it with the Milky Way's own interstellar matter. This transfer of material provides fresh fuel for the birth of new stars, keeping star formation alive for billions upon billions of years. Sometimes the gas torn from these dwarfs forms massive clouds that race through space at incredible speeds, much like the mysterious high-velocity clouds astronomers observe today. These moving clouds influence the vertical motions of gas and stars in both the halo and the disk. And what makes this even more fascinating is that such events are not just ancient relics, they are happening right now. Observations clearly show that several dwarf galaxies are currently merging with, or being swallowed by, the Milky Way's halo. The importance of these dwarf galaxies goes far beyond the gas and stars they bring. They give astronomers a direct window into the process of galaxy formation and the evolution of the entire cosmos. According to the widely accepted model of cosmic growth, large galaxies like the Milky Way were not born in an instant. Instead, they slowly took shape over billions of years by absorbing smaller galaxies one after another. The dwarf satellites we see today are the surviving fragments of that ancient process, the leftover building blocks from which our galaxy was assembled. By studying their masses, the elements that make up their stars, and the paths of their orbits above and below the galactic plane, scientists can test ideas about how galaxies grow and learn how the Milky Way itself came to be. Many of these dwarfs follow long and looping orbits that carry them hundreds of thousands of light-years away from the galactic disk deep into the halo, where they act as silent witnesses to the Milky Way's gravitational power and its long history of encounters with other galaxies. These small galactic companions are also key to understanding one of the universe's greatest mysteries, dark matter, the unseen material that makes up most of the Milky Way's mass. As dwarf galaxies move through the halo, they behave like natural probes, tracing the pull of both ordinary matter and dark matter. Their paths, the way their shapes are stretched by gravity, and the faint trails of stars they leave behind reveal the shape and thickness of the invisible dark matter halo surrounding the galaxy. Those dwarfs that travel in polar orbits, moving high above and far below the galactic disk, offer a clearer view because they explore regions of the halo less disturbed by the bright ordinary matter concentrated in the disk. By observing these systems, astronomers can refine their understanding of how dark matter interacts with normal matter and how it guides the formation of galaxies across the universe. Some dwarf galaxies are especially striking in their interactions with the Milky Way. The large and small Magellanic Clouds, for example, are now being slowly torn apart as they orbit around our galaxy. They have left behind a vast 600,000 light-year-long ribbon of gas known as the Magellanic Stream. This enormous structure shows how dwarf galaxies feed material into the halo and reveals the Milky Way as a truly three-dimensional dynamic system, rather than a simple flat spiral. Other dwarfs, such as the Sagittarius dwarf and the Canis Major dwarf, are already deep into their destruction, leaving behind graceful streams of stars and debris that swirl and mix with the halo. These ongoing mergers show that the space above and below the galactic plane is alive and ever-changing, a place where smaller galaxies are constantly being absorbed into the greater body of the Milky Way. Beyond their effect on the galaxy's gas and structure, dwarf galaxies also hold priceless clues about the Milky Way's ancient history. Many of them contain very old, metal-poor stars, preserving the chemical fingerprints of the earliest generations of stars in the universe. When these ancient stars are stripped from their parent dwarfs and spread into the halo, they enrich the Milky Way with the oldest stellar populations, creating a living fossil record of the galaxy's youth. By examining the ages, elements, and locations of these stars, astronomers can piece together the long timeline of how the Milky Way formed and how star formation has changed through cosmic time. The presence of all these small satellite galaxies around us reminds us that the Milky Way is not a simple, flat, lonely spiral drifting in space. It is part of a vast and complex web of gravity, filled with orbiting companions, flowing streams of gas, and the scattered remains of ancient mergers. These dwarfs are not passive bystanders. They are active participants that shape the halo, influence star birth in the disk, and reveal the invisible structure of dark matter that surrounds everything. By tracing their journeys and interactions, astronomers gain a clearer understanding of our place in this immense galactic system, discovering that our solar system lies within a living, ever-moving, and interconnected cosmic ecosystem that stretches tens of thousands of light-years above and below the Milky Way's shining disk.